again. So good afternoon, or good morning, or good evening to everybody. So this is the final session of the Micropropulsion and CubeSat workshop, the 5th edition. Unfortunately, it went very, very fast, but we had very, very good lectures and talks and invited lecturers. So we will have 4 talks this afternoon until 4 p.m. And at 4 p.m., I remind you that we have a roundtable about technological development and application of micropropulsion with many startup and agencies. So I really advise you to join this roundtable at 4 p.m. That will be chaired by Alberto Rossi from the CNES, and I will be the chairman for this session. So we will start with Alfio Vinci. Alfio, yes? Do you hear me?
Can you hear me? Yes, I'm good.
Okay.
The same
so
for
you.
You
can, yeah, it's fine. You can share your screen.
Okay.
And as you know, you've got 15 minutes, and we will have 5 minutes for questions. Okay.
So, is it good?
It is.
Okay, so I start. All right. My name is Alfio, as Stefan said. These activities I will discuss are carried out at CNRS, ICA, under the supervision of Stefan himself, in the framework of an H2020 named HIPATIA. More specifically, my speech will deal with an experiment that meant to investigate the ion and the electron energy in a magnetic nozzle that features different expansion ratios. The outline of the presentation is as follows. I will describe you the objective of the research, and then I will comment on the experimental setup and the diagnostics we used. And I will finally present you the results and derive some conclusions. So we are all here for micropropulsion, I guess, and it's quite clear that recently this sector is manifesting quite an important interest in electrode-less technology and in acceleration by means of magnetic nozzles applied to different kind of sources. One possibility that we are investigating is helicon plasma thrusters that are mainly studied in laboratories at the prototype level, although some particular devices have been deployed in space. The purpose of our activities is to have an insight into the physics that is ruling this kind of plasma sources, in order to improve the understanding we have of this kind of plasma, and possibly to improve the performance we currently get. This is the setup we have at CNRS. It's a medium scale device. It's useful for studying the fundamental physics. As you see, it comprises a main discharge tube through which the propellant, in which the plasma is generated by injection of the propellant at the backplate. The plasma is generated by means of a double saddle type antenna, and the plasma expands in a relatively small vacuum chamber that features some coils to apply an external magnetic field, as well as it does the discharge tube. For this particular experiment, we decided to fix the input power to the antenna at 800 watts and to fix the mass flow rate at 0.2 milligrams per second of xenon. I mentioned at the beginning, well, it's the title of the presentation is about expansion ratios. So why we should study different expansion ratios of the magnetic nozzle? Let me point out that the thrust given by the presence of the magnetic field is given by this equation in integral form, approximately given by this equation, where appear the radial component of the externally applied magnetic field and the BR and the electron azimuthal electron current density. So what we can think reasoning on this equation is that if we manage to have a constant azimuthal electron current density, and we increase the radial component of the magnetic field, that is increasing the expansion ratio of the magnetic nozzle, we obtain an increase in the obtained in the thrust. Actually, it's not true that we can have a constant azimuthal current, because a larger radial component of the magnetic field has an impact on the overall topology of the magnetic field itself due to conservation of the magnetic flux. So basically, if we increase the radial component of magnetic field, as you can imagine, we decrease the confinement of the plasma, so it changes the radial component of the electric field due to the plasma potential, and it gets different value of the azimuthal electron current. In this experiment, we obtained the three depicted magnetic shapes in the following way. We fix the current at the coil named GB3 to 9 amps, and we tune the current on GB1 to 0, -1, and -2 amps to artificially enlarge the magnetic nozzle. What I was saying about the expansion ratio here is defined as the ratio between the radius of the streamline that crosses the tube edge at Z equals 0, divided by the radius of the discharge tube. And here you have a space evolution of the expansion ratio. In the following, I will refer to expansion ratio or divergence in the same way, like if they were exactly synonymous. So the diagnostics we use to measure the plasma we obtain comprise two elements. The first one is a radio frequency compensated Langmuir probe to measure the plasma density, the electron temperature, the plasma potential, and more generally the electron energy distribution function. And the second one is a retarding potential analyzer to measure the ion energy distribution function. I don't have much time to discuss on the details of this diagnostics, but if you want, you can ask questions at the end of the presentation. So the first quantity we obtained is the ion energy distribution function by means of the RPA. Keep in mind that the energy represented in these plots is the total ion energy, so it comprises the potential contribution to the plasma potential and the kinetic contribution due to the velocity of the ions. The three plots here represent the spatial evolution of the ion energy distribution function as a function of the three different expansion ratios of the magnetic nozzle. So the first thing we observe is that the total ion energy decays quasi-linearly with Z for the three different configurations of the magnetic nozzle. And the second important thing we observe is that the total ion energy decreases as we increase the divergence of the magnetic nozzle. It's probably easier to see it in this plot, which is basically the most probable ion energy extracted from the general distribution function. Commenting on the fact that on previous studies here reported, we performed LIF measurements, we observed that the typical velocity of the ions is relatively small in this reactor, in the order of 0.1 volts, while the plasma potential instead has a typical value of 10 volts. So it's hard to distinguish here if the ions are more energetic in terms of kinetic component when the expansion ratio is larger or not. It would instead require to use LIF again under the different configurations to be exactly sure what's going on in terms of ion velocity. Using the Langmuir probe, we obtained several maps of the typical plasma properties. Here are reported in normalized units to allow comparison between the different expansion ratios of the magnetic nozzle, each of which is represented by a row of this, let's say, visual matrix. We can observe a couple of things from this data. First, that the peak of the plasma density is given in the case of lowest divergence of the magnetic field, as expected, because if we enlarge the nozzle, we decrease the confinement of the plasma. And the peak that occurs off axis, as previously reported many times in several studies, it moves upstream when we increase the divergence of the magnetic nozzle, as you see from these peaks here. They are shifted towards lowest value of Z when we increase the current on GB1, so when we increase the divergence. About the electron temperature, we can observe that the plasma is, the electrons are very well magnetized also in the case of the highest divergence, as you see that the plume is really following the magnetic field lines, which is true also if we look at the graphs of the contour plots of the plasma density. They really follow the magnetic field lines. And about the plasma potential, we can observe that first, the peak of the plasma potential agrees with the peak of plasma density. And a thing that has been commented many times throughout this workshop is that the plasma potential does not follow the shape of the magnetic field in this case. Starting from the radio frequency compensated Langmuir probe, again, we can derive the electron energy distribution function using the conventional method. And you see the results in these counter plots again for each of the values of the divergence of the magnetic field. We can observe an unexpected thing. The first one is that the electrons are cooled when they follow the, let's say, throughout the magnetic nozzle. So they start from a most probable energy of about 4.5 electron volts, and they go down up to 2 or 3 electron volts downstream. These maps are calculated along the axis of the reactor. We can also point out that the broadness of the electron energy distribution function becomes smaller when we move downstream. That suggests that the hotter population of the electrons is cooled down when we move along the nozzle, and also that the broadness again decreases as we increase the divergence of the magnetic nozzle. And you can see this fact from the color legend in this region for the 3 values of the magnetic nozzle divergence. So here, the broadness is lower with respect to here. Finally, perhaps the most interesting result for those who are involved in modeling and simulating the plasma is one of the most debated topic in plasma expansion. That is the, let's say, the thermodynamic analogy of the electrons by means of the polytropic index. So what you can see in these 3 plots is the logarithmic of the electron temperature versus the logarithmic of the plasma density for the 3 types, for the 3 magnetic nozzle we have. In the region where both the plasma density and the electron temperature are decreasing, which is basically the expansion region of the plume. That should match linear law if it is purely a polytropic expansion. This is relatively true for the case in which the current on GB1 is 0 and -2, and it's less evident, let's say, in the case of -1 amp. Theoretically, it has been assumed most of the times that the degrees of freedom of the electrons is equal to 3. That leads to a value of gamma comprised between 1 for the isothermal expansion and 5/3 for the adiabatic expansion. The result in this case is that the best fit of gamma is about 2, which suggests that the degrees of freedom of the electrons is 2 instead of 3. And this can be due to the inhibited cross-field transport of the electrons because of the fact that they are magnetized, basically. So if we look at the electrons expanding through in the reference frame of the magnetic streamlines, it's like if they can just move along the streamlines and spinning about the streamlines, but not moving in the cross-field direction. And this result has been also found in another study recently published in the reference here shown at the bottom. This leads me to the conclusion. What we observed is that in this experiment, that the ion energy typically decreases as we increase the divergence of the magnetic nozzle. This is the total ion energy again. We also have observed that even in the case of greatest divergence of the magnetic nozzle, the electrons are visibly magnetized because they follow the streamlines in the map of both the density and the temperature of the plasma. We also have observed that the electron energy distribution function becomes less broad as we increase the magnetic nozzle divergence. And finally, probably the most relevant result, again, for those who are involved in modeling, is that we found a polytropic index of about 2, independently on the divergence of the magnetic nozzle we have applied. These results would be nice to be, let's say, accompanied by other type of measurements, for instance, thrust or ion velocity measurements using LIF, for instance, which would better give us an idea about what's really going on in the nozzle when we play with the divergence of it. Another interesting thing would really be to measure to directly measure the electron azimuthal current density to see how this is affected by the different shape of the magnetic nozzle, and so to try to get a best configuration in terms of ruined the current density, but increase the radial component of the magnetic field. Thank you for attending this talk, and I'm available for questions if there is any.
Thank you, Alfio. Thank you for this presentation. So
it should be on time.
We have a bit of time, 2-3 minutes for a question from the audience or remark or comments. Yes, we have one. From Timothy. Okay, you can ask your question, Timothy.
Hi, thanks, Alfio, for this talk. This has been really interesting. You mentioned that you're using the Joyvestein technique to look at the EEDFs. I just wanted to ask if you could comment at all on how Maxwellian it looked like your energy distributions were, or if you were able to kind of look into that at all.
Sorry, if you're meaning if this distribution looks like a Maxwellian or not?
That's right. I don't think I saw, I couldn't quite make it out from the image, I guess.
Well, I don't have in this presentation a plot of a single line profile, which would allow us to better to clearly see if it's Maxwellian or not. I would say from what I've seen by post-processing the data that some of them look like Maxwellian, some not, or like a quasi two population situation. But since the energy we have in this reactor is fairly low, well, a Maxwellian approximation in this case, it's good, I would say. In fact, for instance, this data is derived under the Maxwellian hypothesis, and the fitting, I remember it was quite okay.
Thanks so much.
Okay, so we have another question from Jacob.
Hey, thank you very much for the talk. Very interesting. I think I saw in an earlier plot that the ion energy was decreasing with the axis.
Yes.
Why is that happening?
Well, as I said, this is the total ion energy, and in our reactor is mainly how can I say, the larger part of this value is given by the plasma potential. So it's most likely that this decrease is due to the decreasing of the plasma potential, because the potential contribution is much larger than the kinetic contribution in this case.
So this is the total ion energy, not just the kinetic?
Exactly.
Oh,
This measurement is referred to ground potential.
Gotcha. Okay, thank you.
Okay, the last one. No, perfect. Let me check. So thank you again, Alfio, for this talk on magnetic flow. So we're gonna switch to the next speaker, Benjamin John from Michigan. Benjamin, it's up to you. Okay, we see your slide. It's perfect. Okay, so you've got 15 minutes, Benjamin.
Okay, thank you. Stefan said, my name is Ben Jorns. I'm a professor at University of Michigan, presenting this work primarily done by a doctoral candidate, Ben Wax, in our research lab. The focus of this talk is to discuss some strategies we've been exploring to combat one of the major technical obstacles for developing low power magnetic nozzles. And low power in this context, I mean less than 100 watts. And specifically, we've been exploring strategies based off of power conditioning, how we can change the frequency of injected radio frequency waves and use multiple frequencies or potentially chirp the power in such a way that we can combat traditional loss mechanisms, including low mass utilization and overwhelming losses to the walls. So to motivate this work, I take a step back and talk briefly about the principal operation of nozzles and in turn, why they're attractive for small satellite applications. And to that end, I'm showing here a canonical geometry and cross-section of a nozzle on the upper left-hand side, which has 4 key elements here: that the strong magnets, permanent in our case, applying a diverging magnetic field, a source for radio frequency energy from the upstream location, which is then injected into a propellant flow stream. And then the downstream component of the magnetic field is characterized by a diverging geometry, which facilitates the conversion of thermal energy into kinetic. And indeed, to this point, these devices are inherently electrothermal in so much as they rely on the introduction of strong thermal energy, particularly in low power cases, into the electrons, which is then converted into directed kinetic through ambipolar effects as those electrons are expanded along the diverging geometry, cooling down, leading to a potential well, which in turn accelerates the ions. So the major advantages of this technology from the perspective of small satellite propulsion are: 1, its simplicity, which lends itself to manufacturing at the small scale. 2, by its nature, it's inherently magnetically shielded in so much as the propellant is kept away from the walls, and therefore in principle can work on more exotic propellants, which are attractive for small satellite applications like liquid storable propellant configurations. And then finally, it's cathode free, which offers a nice advantageous contrast to gridded ion or Hall effect thrusters as they're scaled down in size. Now, I'll say operationally, there are a couple magnetic nozzles at the low power regime that are flying on orbit as we speak, but there still remain some technical challenges, at least historically, which stem from the fact that over the past 10 years, the performance has seemed to cap out at around 10% for configurations that are less than 100 watts. Though, as we saw yesterday, it seems that there has been a recent breakthrough, which has improved that efficiency by a factor of 5, and I'll touch upon that in just a second. With that being the case, I do want to talk briefly about why these efficiencies are so low, or at least they conventionally have been, and then what strategies that recommends for how we may ultimately improve them in such a way that this technology becomes more competitive and therefore potentially more pervasive for small satellite applications. So the first major efficiency channel loss that's known for these devices is the mass utilization. And to illustrate that, I'm just showing graphically here a zoomed in view of the discharge chamber where the majority of RF energy is introduced. And effectively, qualitatively, what happens here is in these devices, as propellant is flowed in through the upstream, it encounters the RF energy, in this case injected through a coaxial antenna, which serves to ionize the propellant as the free electrons are heated. And in practice, it turns out that some of those neutrals are converted into useful plasma, which can be accelerated by the magnetic geometry, but there are some residual neutrals left over. And in practice, it turns out that the mass utilization for some of these systems can be as high as 70%, but also for many systems can be as low as 10%. And that mass utilization tends to drop as you go to lower powers. Now, that in part can be mitigated by running at effectively higher powers compared to the input flow rate. This should make intuitive sense as you're providing more effective energy per input neutral. And indeed, that's been demonstrated in the past. I've drawn a result here from work performed at Onera, where they looked at the different efficiency breakdowns, plotting here, in this case, the mass utilization efficiency as a function of the flow rate compared to the power. This can be seen as you drop the effective flow rate for a fixed level of power, the mass utilization does ultimately increase. But as you can see in this particular example, the mass utilization at those lowest supportable flow rates was still peaking at about 40%. So while it remains true the mass utilization may not be the dominant driver, it is still an important driver for reducing the efficiency of these systems at low power. The other potentially more dominant driver is wall losses. And to illustrate that, again, I'm showing a zoomed in view cross-section of the discharge chamber of the system, and in turn color coding the different power fluxes to the different elements of the geometry, where black denotes power losses to the walls, blue is power loss to the back wall, blue is power losses to the walls, and red denotes useful power, which is transmitted downstream. As with all systems, gridded ion and Hall effect thrusters, as you scale them down to size, you ultimately combat challenges related to the area to volume ratio, where increasingly more plasma can ultimately flux to the external geometry, giving rise to effectively lower efficiencies. And indeed, it's been shown through modeling work that this is still a dominant driver as well for these low power magnetic nozzles. So you can see on the left-hand side, I've color-coded this for a result drawn from work performed by LaFleur, where you see the dominant efficiency driver is captured by blue here as the losses to the walls. So taken together, these mass utilization and the effective wall losses represent probably the dominant drivers for low efficiency at low powers. And just as with mass utilization, there are some design strategies that have emerged from modeling efforts that may help combat this. For example, moving to stronger magnetic fields can reduce flux to the walls, therefore raising efficiency, or you could just adopt a larger geometry. But the challenge, particularly for scaling down to small satellites, is that these solutions may not be feasible or practical for small U footprints. The magnetics that you employ may not provide strong enough magnetic fields. And alternatively, the geometry of the thruster becomes prohibitively large if you scale it up in size. So the overarching question that we've been trying to address, as have others in the community, is that in order to improve efficiency at these low power and size required for small sat applications, are there strategies available to us that may not have been explored for increasing these two dominant traditional efficiency loss mechanisms? So the first strategy, which has been explored parametrically and extensively by Onera, is to look at different combinations of material and geometry, as shown here qualitatively. They've done a quite extensive investigation over multiple years through the Minotaur project that we heard about yesterday, looking at different channel geometries, different channel dimensions, different materials, and different RF coupling schemes facilitated by the choice of different antenna. And indeed, what's emerged from this is that, to my knowledge, in published work up to 2018 and 2019, they demonstrated they were able to increase efficiency from 2 to 3% to 10%. And that was what was thought to be the state of the art. But we did see yesterday that they've continued to iterate upon this. And apparently there's this breakthrough demonstration of efficiencies exceeding 50%. So that really underscores the point that some of these manipulations have been able to give rise to really strongly competitive performance. Of course, I won't talk about this particular strategy at more length today, because we've been exploring a different tact, which has not yielded the same degree of results, but does seem to be providing significant improvement and promising improvement in the direction of improving efficiency also. And that strategy that we're exploring in Michigan is one based off of power conditioning. So instead of manipulating the geometry of the system or changing the materials in order to combat wall losses and improve mass utilization efficiency, the premise of our approach is to try to manipulate the RF scheme injected into the system in such a way that we can improve the mass utilization and reduce effective wall losses. And the strategy that we're employing is based off of the electron cyclotron resonance heating scheme. And I'll touch briefly upon why this can be manipulated in ways we think they could ultimately improve efficiency. So there are kind of three strategies we have in mind. The first one is if you are able to inject your power along center line of the thruster, then in principle that should help mitigate heat flux to the walls. And as a direct consequence would lead to lower temperatures along the walls and therefore lower energy flux to the systems. So the first idea here is that if we can just control geometrically the power deposition from the RF heating scheme to be on center line, that could in principle lead to lower wall losses and higher efficiency. A second additional strategy for improving mass utilization is that if we can extend the region of resonance or power deposition to be further downstream and elongated, that should give a higher likelihood of ionization for neutrals as they cascade downstream. And therefore increase the mass utilization efficiency. And then finally, one strategy that we have discussed in theory but have yet to demonstrate in the laboratory is chirping or pulsing the discharge. And the advantage of this is that in principle, we think that it should allow us to break free of some of the traditional paradigm limitations that emerge from the paradigm of just having a steady state power balance. And to kind of underscore that, I'm showing this analytical expression here, which suggests that the efficiency should scale inversely like the area ratio of walls to exit plane. That's really the wall loss term. The frozen flow losses are related to ionization energy, the second term. And then that last term represents the rate change of the temperature or plasma pressure in the system, which in steady state is assumed to be zero, but if you do allow for pulsing of the power, that can become a time-dependent term. And in principle, just mathematically, if you're able to make it negative, that may be able to drive up the efficiency. So kind of armed with that qualitative insight, our overarching purpose has been to explore strategies in which we can facilitate these different schemes for facilitating, in turn, the targeted spatial introduction of power into different regions of the system and temporarily changing it. In particular, what I'll focus on the talk today is work that's been done by Ben Wax to look at these two spatially related effects. So the approach that we apply to that is to leverage the properties of the electron-cyclotron resonance heating scheme for geometry and to talk qualitatively about how that's accomplished. I'm showing here a zoomed in view of the thruster with the magnetic field lines going downstream, and shown in color on the color scheme is the magnitude of the magnetic field. And the central takeaway here is that the electron-cyclotron resonance should scale linearly with that magnitude of field. Now in the ECR scheme, the idea is if you do not have an overdense plasma, you'll have an absorption of the injected RF waves represented here by the sinusoidal pattern at the magnetic surface, which corresponds to the electron-cyclotron resonance scheme. In that case, that's where the frequency of the injected wave is equal to the local electron-cyclotron frequency. So in this case, we might have absorption along a given contour of the line. This mechanism for absorption at that targeted frequency allows for the ability to manipulate spatially where that absorption is occurring. So if you are able to change the frequency of injection is shown here, you effectively can move where that resonance zones occurs, and therefore spatially where in the discharge you're injecting power. So that checks the box, at least qualitatively, in being able to control spatially where the power is injected in the system. The second strategy is to inject multiple waves, and this goes to the second approach that we talked about qualitatively about improving mass utilization. And in this case, if you inject two frequencies into the system, that will lead to two resonance zones, and therefore can, in principle, protract the region of ionization of the system, therefore potentially picking up some neutrals that have not been ionized in the downstream region. We'll say here as well that the strategy came to us from the electron-cyclotron resonance ion source community, where their application is more for etching and materials processing instead of propulsion, but they've used these multiple frequencies and been able to demonstrate the generation of very high energy ions and doubly charged ions. So with all that being the case, I think qualitatively the fundamentals of the approach are established, but in practice, it turns out to be more challenging in actually establishing what frequencies are optimal for potentially improving the efficiency of the system. And indeed, this invites a question of dimensionality, where even if you have two frequencies, in principle, there are an infinite number of combinations of frequencies that you could explore to try to see how it improves efficiency. So that lends itself to the last part of the talk here, where I want to talk about our strategies for trying to explore that parameter space. So first, let me say a quick word about the test article before I talk about the strategy of optimization. This is our magnetic nozzle shown here on this chart and in 3/4 view on the upper left-hand side. You'll see that it looks familiar to the designs that were presented yesterday by Onera. It's largely inspired by that. And you can see that some of our characteristic geometries are also drawn from their previously published work. It's about 2.8 millimeters in diameter. We use gas xenon, which is circumferentially injected. For this test, we operated at 30 watts and 1 SCCM flow rate. Our maximum magnetic field was on the system was on the order of 1,000 Gauss, and you can see here the frequency ranges that we explored range from 800 to 2,500 megahertz for both the 1 frequency and 2 frequency coupling cases. All this testing was done in our junior test facility. It's a 1 meter by 3 meter system. It's capable of base pressures when the thruster is flowing gas of less than 10 to the -7 torr. And then finally, our thrust stand is an inverted pendulum stand with sensitivity less than 0.1 millinewtons. And the capability I'll emphasize here is that it's able to turn around measurements very rapidly. So we're able to generate thrust measurements on the time scale of less than one measurement per minute, which is important from the optimization perspective. So armed with this experimental setup, the optimization strategy here we defined was to try to optimize the objective of the efficiency, calculated in this case directly from the measurements from the prescription given here. So we can calculate the thrust, so we know the flow rate and power, we know directly the efficiency. And the strategy is shown here in block chart form, where the first step, we input a frequency combination in the system. We allow the system to equilibrate for a couple seconds, then we take a performance measurement. We input the resulting measured efficiency into an optimizer, generating a database of the efficiency as a function of frequency combination. And then we use a non-gradient based optimizer to elect and to identify a different point in parameter space to try and repeat the cycle, doing this hundreds of times in order to populate the parameter space of efficiency. So with that algorithm in mind, I'm going to jump to the results here. The first one is more of a proof of concept, which is just demonstrating single frequency optimization. And what I'm going to show here is in real time or sped up time, the iteration of the optimizer on the bottom axis, and then the frequency that's injected on the top axis, and in turn, the efficiency that's measured as a function of time. So you'll see that evolve. And what's happening here is that the system is autonomously exploring parameter space, looking at different combinations, changing the operation of the thruster, trying to drive it to a higher efficiency. And you can see ultimately on the steady state result shown on the next chart that as it continues to iterate, it does improve the efficiency. So the major takeaway is that just by changing the single frequency input of the system, so we're not doing 2 frequency in this case, just changing a single frequency of the ECR microwave source into the system, we're able to affect an effective increase in efficiency by a factor of 2, leading to these performance measurements shown here. But we're still kind of capping at that historical 10% efficiency that has existed previous to the results that we saw yesterday. In this case, we did 34 measurements in 45 minutes. And really, this is more of a proof of concept because we could have accomplished the same goal just by doing a parametric systematic investigation by changing frequency. I'll make one comment here about the physical intuition implications of this result. What we ultimately found is that we had the optimal efficiency when the frequency of injection was equal to the cyclotron resonance zone that is directly coincident with the upstream region of the thruster, which in turn suggests to us that you get optimal performance when the resonance zone is as far as upstream as you can make it. We think that this might have been a conclusion that had already been reached before in previous studies, because if you do look at some of the work that's been performed by Onera, they have their resonance zone quite close to the upstream injection plane. I think it's an open question to us why this leads to better performance, but the parametric results do seem to show that, and that's potentially a subject for future exploration. The next thing I'll talk about here is 2 frequency optimization. And in this case, following that prescription, we're exploring autonomously in parameter space, different frequency combinations, trying to improve efficiency. And so what you're seeing here is now 200 iterations, and the optimizer is systematically stepping through space, trying to identify the regions that lead to the optimal performance. And the map here on the upper left-hand corner is giving you an indication of the measured efficiency for those different frequency combinations. So again, this is very sped up. This actually took 3 hours to do this test, but you can see that we're steadily marching forward in terms of performance. The actual results here and their physical implications are illustrated on this next slide, where on this contour plot, we have frequency of injected frequency on the x-axis and on the y-axis. And then you can see the contours for efficiency that's measured on the plot. And what it illustrates here is that in our case, we were getting optimal frequencies, actually optimal efficiency when the two frequencies were equal to each other. And again, when those two frequencies were equal to the maximum frequency we could achieve, which in turn was coincident with the backplane of the thruster. So again, with this iterative process, we were able to improve the overall efficiency from its lowest point by a factor of 2. And that underscores the point that the frequency of the injected power is a significant driver in the performance of these systems. But significantly, in our case, it looks like using a 2-frequency scheme actually does not improve performance. And so that kind of second governing hypothesis that was driving this work initially, that by protracting the resonance zone by introducing 2 frequencies, does not at least seem to be viable from this preliminary results. In other words, instead of spreading out your resonance zone, your best strategy, at least our preliminary results indicate, is to inject all your power at the upstream location, and to, if you have a finite amount of power available, to put it all there. So this invites a question, of course, is 2-frequency beneficial? But I'll say here that the parameter space we've explored is fully not comprehensive yet. There are many more frequency combinations to try in how we apportion the power to each of those respective frequencies. So that brings me to my conclusions here. The first couple bullet points are just reiterating the motivation for this work. Leaving to that last one here, I'll say that our approach, instead of kind of exploring different geometry iterations, is instead to focus on the power conditioning. And by employing a surrogate-based optimizer, we've been able to demonstrate we can improve efficiency by a factor of 2. And this has led to follow-on work where we'll continue to expand the parameter space, but also explore that third strategy that I mentioned at a high level, which is chirping the power into the system, and see if in turn that allows us to break free of the limitations of the current paradigm of steady state power losses. One final note here, and this is just invited by the results that were shown yesterday. We have a lot of similarities with the Onera design. In fact, that's been a guiding light for us in putting our test article together. But we haven't landed on the secret sauce that gave that 50% efficiency. So it's a really exciting result to see, and hopefully something we can talk about at more length in the future. So with that, I will thank you for your attention and just acknowledge the funding source, which is a NASA fellowship won by Ben Wax, who just concluded this year, and he'll be graduating here in just a couple months. So again, thank you for your attention. If I have time, I'd be happy to invite questions.
Thanks a lot, Ben. This was really, really very interesting, really great. I really like it. Very, very interesting. That shows that there are still many things to do and to understand in this field. We have a question by Evgeny.
Hi, Ben.
Hi, Evgeny.
As always, very good presentation. Thank you. So I start from technical questions. So if you're going to lower frequency than 2.45 gigahertz, which Onera folks use, so what about feasibility, cost, and complication of the power source which you will have for CubeSat? Because I mean, for ground, of course, it doesn't matter. But for CubeSat.
Yeah. If I'm hearing your question right, what about the limitations of power supply and actually generating these frequencies for a real application?
Right, like lower than 2.45.
Yeah, is it feasible? Is the question? I guess
it's feasible to make compact for CubeSats. I mean, is it practical for CubeSat?
Yeah, I don't know. Maybe. I think that I would probably say right now, no. I'm not sure there are flight qualified systems that have sufficiently small footprint to support that. And I think that's an open question that's being looked at by other people exploring this technology. So kind of an interesting idea is we could inject that as one of the constraints in our optimizer to say you could go, given current technology, what frequencies should we actually be exploring? So that could limit the parameter space. But short answer to your question is I'm not sure that there are actually available technologies that could be scaled down, right off the shelf to support those lower frequencies.
If I may, one more question. So basically, having ionization region next to the backplate should actually cause erosion and lifetime issues, right? Because ions will get accelerated back. Of course, they will produce thrust, right? By bombarding the wall. So this is what I didn't understand from Onera. I mean, they talk about lifetime expectations. So, so any comments about?
Yeah, I mean, we haven't run. Sure, we haven't run enough to actually really show significant erosion, except for when we have an antenna and they're made out of a more sputterable material like copper, in which case you will see substantial erosion on that. And then the strategy that they've identified is to mitigate what's the most apparent erosion process, which is the antenna itself, and they're looking at just making it thicker so you have margin. We actually have a graphite antenna, so that it even has lower sputtering. Kind of looking at that downstream question. I think, but your other question was kind of about the erosion of the upstream plate. And that one, I'm not sure what the answer is there, because as you say, you have such a hot plasma there, you would anticipate having pretty substantial sheath drop to that backstream region. So that could also pose a life-limiting mechanism. I'm not sure that's actually been identified or shown conclusively from the limited life tests that have been done. So maybe material choice, maybe something clever by changing the magnetic topography so that you can leverage maybe some of the principles that were identified from magnetic shielding and hollow thrusters. So you have a cold field line to facilitate lower sheath drops to the walls. But yeah, short answer to your question is I think it's an open question as to what the erosion processes are on that back plate.
Thank you very much.
Yep.
Okay, so we have a question from Ashley.
Okay,
Hi.
so
Yeah,
Can you
Ashley.
hear me?
Yes, we can.
Hi, Ben. Nice talk. Gosh, you and Yevgeny must have gotten up really early today. My question is, have you considered adapting the magnetic field topology so that the ionization volume increases? So the volume where the magnetic field is the right value is larger.
Yes, so that's an idea that Ben, the student who's worked on this, has been kicking around, and he has a couple ideas for different geometries for accomplishing that. One of the challenges that's posed is trying to accomplish that with permanent magnets. So you can be clever by how you configure them to generate some geometries where you have kind of a protracted resonance zone. And in fact, that's a strategy that does come from the ECRIS community, where you kind of have a clever geometry so that you have a more spatially protracted resonance zone that's not just characterized by a kind of fixed plane, as I showed earlier. So short answer, again, to your question is that yes, we are looking into that too.
Okay, we have a question from Victor from Onera.
Okay, hello Ben, thank you for your presentation and work. It was very interesting. We've been thinking as well, of course, of training several frequencies. And one of the problems we encounter is how to mix these frequencies and how to be able to measure precisely the power that you are actually injecting with each of those two frequencies. So can you maybe a bit comment on the experimental setup, how you manage to do these measurements with a good accuracy, because it's very important when you are going to compute an efficiency of a cluster.
Yeah, so I'm able to answer this question in 30 seconds, but it's really a credit to Ben who beat his head against this problem for a year. The shorter answer is that if you use kind of conventional power coupling measures, which are designed for one frequency, they're not accurate. So he set up a system where the power sensors are based off of the thermal loading on the power sensor. So we still do a reverse and forward detection of the total RF power going into the system, but we characterize that after it goes through the directional coupler by measuring effectively the increase in temperature that it's terminated into. And so the advantage of that system is that it tells you the total power that's forward and reflected without having to leverage kind of a knowledge about what the input frequency is. When we didn't do that, we were running into challenges where we actually didn't know how much power we were coupling in the system. Ben has a nice paper at the recent P&E results where he talks about the different components that he used to set up that system, and I'd be happy to share that with you.
Okay, yes, thank you very much. I'll be happy to read this paper. Yeah, thank you.
Okay, thanks again, Ben, for this very interesting talk with many reactions from the audience. We are a bit late, so it's time to switch to the first speaker. So the first speaker would be Andrei Smolakov from Canada. Andrei. Where is Andrei? We lost Andrei.
No, I'm here. So I can share the screen now?
Yes, you can. Okay,
Okay.
it's working.
Okay.
Okay, it's up to you, Henri.
Yeah, thank you very much for invitation. And I'm going to talk about some features of plasma flows in magnetic nozzle. This work has been performed by in collaboration with some group of students and as well Peter Yushmanov and Sergei Putvinsky from Trialpha Technologies. So the point of this work actually is very simple. I would like to discuss this issue. Yeah, let me just use a laser pointer. So this is in red. This is actually conclusion, important conclusion that the condition at the nozzle throat, and for magnetic nozzle, it's a region of maximum magnetic field, defines a global solution. And this property, though it's well known for Laval nozzle, I don't think it has been discussed properly in the community. So for this talk, I will generally show some exact solutions which can be obtained for cold plasma, cold ion limit, and then this exact solution nicely illustrate this property. And then I will show how this cold ion solution can be modified with warm ion effects as well as some kinetic effects. So like I don't need to talk about motivation, propulsion. For us, in fact, one of the motivation was using magnetic nozzle as a natural diverter in open mirror system. So that's as you can see, this is a nozzle, and the property of plasma flow in this nozzle are important for device operation. There are a couple of devices involved which have been built and exist. This is device at normal device at Alpha Technology, and then there is some kind of secretive device at Lockheed Martin. It's all open mirror system which have a magnetic nozzle at the end. So the first, like a simple model for cold ions is very standard. It's nothing new here. It's well known. Like in this case, I'm using paraxial model, so it's like a narrow tube. It does take into account two-dimensional effects, but then after some expansion, it reduces to one-dimensional model. The electrons are Boltzmann here, ions are magnetized, and this is important constraint, also important limitation, which probably may not be true for some cases, but so essentially assumption here that ions flow along the magnetic field line. And that electrons are Boltzmann and with constant temperature. So like these are simple equations which have been published in number of papers. And the point that this equation can be integrated, solved, like when you do one-dimensional quasi-neutral paraxial model, then you get some equation which is also well known. It's well known that in the quasi-neutral approximation, this equation has a singularity at sonic point. That's a point where plasma flow velocity is equal to sound velocity. And this singularity can be removed by requesting that at this point the derivative of magnetic field is zero, so it basically makes a throat nozzle for Laval nozzle, and with magnetic field is just a region point of maximum magnetic field. And then at this point you can define accelerating solution which exists when magnetic field there's a maximum, that's a condition. And this apparently this equation has a solution in terms of special functions, which is called a Lambert function. Lambert function is solution of this equation. So W of y, you resolve this equation, and then eventually what it gives us solution for plasma flow in terms of magnetic field. And the profile is actually hidden here. So for example, here you have several examples for magnetic field nozzle. So this is a symmetric nozzle. Then depending on this profile, you get velocity profile like this. and then it generates density profile, which is shows acceleration and potential like this. So this solution, the one I'm talking about, it's a unique solution, accelerating solution, which for Lambert function consists of two branches. It has two branches in the real plane, and then they matched at the throat. So this is a sonic point, and then this is a subsonic area acceleration, and this is a supersonic. So in this case, the acceleration occurs in both, like in subsonic region and supersonic, and the condition at the sonic point fully defines the solution. So this is the very important conclusion. For instance, here, like if you change your magnetic field profile, the condition, in this case, the sonic point is the half wavelength, so it's here. The velocity in at the entrance of the nozzle and velocity at the exit are fully fixed. So that's a most important conclusion of this simple model. And in this solution, the only remaining parameter is density at the entrance of a nozzle. So of course, like these are solutions for isothermal case, and it can be easily generalized for non-isothermal case with kind of arbitrary polytropic coefficient. This example again has the same property. In this case, there are different cases of different gammas, starting from isothermal gamma 1 and then 2.3. You see this is a velocity as function of a distance. Again, the solution is fixed here, and you don't see here difference. There is because of scale, the velocity at the entrance point and velocity at the exit point are fixed. And of course, that generates a very interesting question now, how this global solution, how this is a very rigid solution for the velocity, how it is matched to the source region where you generate plasma, and then presumably you start accelerating plasma from basically zero velocity. And to look at this, we developed a kinetic model. So where essentially we use the Boltzmann electrons, but ions now are kinetic, and we generate some ions, like some source with arbitrary distribution, and this is a nozzle we use. It's a symmetric nozzle, and then we want to look what happens if I try to inject plasma, roughly saying with wrong velocity, what happens. So these are these should be sorry for this. I think, do you see my screen, right?
Yes.
Yeah, so I'll show it on this screen. So this is the solution we get in kinetic code, kinetic solution, where we inject ions at this end with some basically arbitrary distribution we can choose, and it's an initial value problem. So the solution establishes it runs. So here is the density. You can see this acceleration occurs because then density decreases with distance. Here's a perfect velocity, accelerating velocity, which sonic point is somewhere here. In this case, ions are warm, so this is actually perpendicular pressure. You see this enhanced pressure here due to an effect of adiabatic moment conservation, and this is parallel pressure, which is drops. So this solution is similar, kind of looks similar to cold ion case, but This is just a snapshot from that solution. In this case, we injected with low ion velocity, so it should be similar to fluid solution. And indeed, we see this nice agreement between cold ion theory and numerical solution. That's a profile of accelerating ion velocity. But even in this case of very cold ions, we see the ion reflection. So in this case, you can see this is a phase space. So it's a ion velocity here. This is distance. So you can see that a fraction of ions actually starts to reflect and goes back into the source. And some ions penetrate, and these ions which are penetrating follow the our analytical solution. We investigate the effect of finite temperature, so we increase ion temperature, and then we see effect of increase of exhaust velocity by enhancing ion perpendicular pressure. And again, so this is a cold ion solution. This is the solution in kinetic theory. This solution we can reproduce from fluid theory. But in this case, now we see the more and more reflection occurs in ion space. You can see that this phase space shows that there are a large number of ions with negative velocity which go back to the source. So that's a sonic point is here, and then these essentially represent trapped ions which are reflected. So if you try to inject with wrong velocity, like in this case we try to inject with velocity which exceeds ion sound, so then you have very large reflection occurs. So this is a phase space plot, and you can see that there is a region of potential which reflect those ions which do not follow this very robust rigid solution. And then fraction of ions which still penetrate again follows the same analytical solution. So that's a demonstration that this solution we get is very robust, and the condition at sonic point defined this global solution. So this is actually a summary. The quasi-neutral accelerating potential structure is formed near the mirror magnetic field maximum, and the regularization condition at sonic points defines the velocity profile globally. So basically at any point along the profile, and some results which I didn't discuss in details, but if you take into account finite ion temperature, then perpendicular ion pressure temperature increases ion exhaust velocity. The final exhaust velocity as well as entrance velocity is a unique function of electron ion temperature, and the profile. Because in this case, the only parameter which remains free is plasma density. So basically total plasma flux, therefore thrust is controlled by plasma density in the source region. And then kinetic solution confirms this model, but of course a fraction of ions is reflected in this case, and the adjustment to the fluid robust solution occurs at the expense of reflection of some fraction of ions due to formation of trapping potential which reflect ions. And then total flux ions is reduced, and density in the source region is increased. There are some publication. So again, the point that when we show this the nozzle, people pay attention to this region often, right? That's how typically it's shown. But what I'm saying that the condition at the maximum magnetic field actually defined behavior in this region, in the divergent region, and these solutions globally defines the whole solution, or condition at this nodal point defines solution. So that's it. Thank you very much.
Thanks a lot, Andrei, for this talk about the physics of magnetic nozzle. Are there any question or reaction from the audience? No. I have a question, Andrei. So you presented comparison with between your model and numerical simulation. But do you have experimental data? Do you have also measurement outcome that really show that the model is correct?
Yes, yeah. So there is this paper which can raise many issues and questions. They were looking for double layer, accelerating double layer, and didn't find it. And so this is actually quotation from this paper. And so this really, like, our work basically provides explanation for these results. That's one paper I know. There is another work which I don't remember the other citation is in our paper, that the region of formation of accelerating potential occurs in the region of maximum magnetic field, and location of that region defines the position of accelerating point. So there was some work done, like playing with this geometry, magnetic geometry, and that changes this accelerating potential. So that's, I think there is some evidence of that this solution is very robust solution, and it exists, can be looked at experimentally.
Okay, thanks, Andre. Any further remark from the audience or the panel?
I had a question, Stefan.
Yes, please, Ben.
So it's really nice work, Andre, and this nice way to simply represent the dynamics. I had a quick question about the assumptions underlying the ion and the electron models that you use. What are you making any strong assumptions about the electron heat flux? And if you do, does this conclusion about kind of the profile being prescribed everywhere just by the sonic condition change? Are you assume adiabatic or isothermal or some mix in between?
Yeah, that one, if we work with generalized polytropic coefficient here, the conclusion doesn't change. So, I mean, it modifies. You can see that gamma 1.3 reduces exhaust velocity, so that's a kind of cooling effect. But condition, the statement of rigid solution doesn't change. It's more sensitive to the assumption of ion magnetizations. This model is for fully magnetized ions which follow magnetic field lines. But like we have some work going on. But the point is that, if this thing works as a nozzle, right? So nozzle, like a Laval nozzle, that's a classical example. And then this constraint will exist. So the things will change if you allow non-magnetized ions, but if the whole thing quasi-neutral, you want to accelerate quasi-neutral plasma using a nozzle idea, and nozzle idea is converging, diverging, then this constraint will exist.
So this is a quick follow-on question. It's interesting that the solutions only diverge downstream, and it seems like the thermodynamics of the electrons does not seem to have an impact upstream of your z equals 0.
No, it does. It does. See,
it just varies.
You don't see, here's a scale. So this zoom in this region. So the solution in upstream also different.
Okay, thank you.
Okay, so let me check. There's no other question from the audience. Okay, so thanks a lot again, Andre, for sharing this work with us. And now it's time to move to the last talk of this session. That would be the last talk of today. That would be the last talk of the micropropulsion in CubeSat 5. So the talk will be given by Yevgeny Raitsev from PPPL.
I'm presenting this one.
Not sorry, Jacob. Sorry. On my paper, it was written Yevgeny's. Sorry.
He's co-authored.
Okay. Yeah, I know. Okay, so the paper will finally be presented by Jacob Simon with the last speaker of today and the last speaker of this conference. So Jacob, you've got 15 minutes.
All right. I don't have the video or anything, or the ability to share right now.
Wait,
probably because Yevgeny was.
Oh, yeah, but I will. Okay.
What's the problem, Jacob?
Thank you. All right.
No, it's okay. Now you have the right, Jacob, right? You can
All
change
right.
now.
There we go.
Okay. Yeah, we see the screen.
Fantastic. Okay. Hello, everyone. My name is Jacob Simmons. I'm a PhD candidate under Evgeny Reitzis at the Princeton Plasma Physics Laboratory. And today I'm going to talk to you about some of our work on miniature wall-less Hall thrusters and the method we've been developing to improve their efficiency. And by the end of the talk, I'm hoping to convince you that the addition of segmented electrodes improves the efficiency not only of large annular Hall thrusters, as has been used in the past, but also of small, low-power wall-less Hall thrusters applicable for CubeSats. And to begin, I'm going to go over some background about why we're on this path. The motivation behind this research is largely involved in trying to understand how to overcome some of the physical limits of Hall thrusters. To the top right, I have a sketch of a conventional annular Hall thruster channel where we're looking at a cross-section of half the channel. Half of the thruster. The dashed line is the axis, the tan blocks are the ceramic channel walls, and the curved blue lines represent the magnetic fields. But as all Hall thrusters are miniaturized, or when the power of thrust density is increased, erosion due to high energy ions impacting the channel walls can become a limiting factor in the lifetime of the thruster. And additionally, plasma wall losses can lead to drops in efficiency as the electron energy is lost to the channel walls, which can cause unwanted heating of the thruster and compromise important components such as nearby magnets or sensitive systems in the spacecrafts, batteries, computers. So several alternate designs have been developed to overcome these problems, and notably magnetic shielding of Hall thrusters, where the channel walls and the magnetic fields are shaped to be parallel to each other, as shown here. The intention here is to reduce plasma flow to these channel walls, and it's seen quite a lot of success. It's been pursued by several research groups and government organizations. Another method is to remove the inner channel wall, which tends to be the area with the most heating problems. This is the cylindrical thruster, and removing this part of the magnetic fields changes the magnetic field profile because you're removing part of the magnetic circuit, and alters the operation of these Hall thrusters quite significantly. And this has been investigated by many research groups. Here's a few of them. And is still quite largely not understood. And another method following the same sort of principle, but this was actually made first several decades ago by Kapulkin, and has seen quite a lot of interest since by several groups such as our moderator, Stefan. I think I saw Barak Karadag in the audience, and our own group. And this is the wall-less Hall thruster. And I'm going to talk a little about how this works. So in an annular Hall thruster, the electrons in the plasma are confined axially by the magnetic fields and radially by the sheaths on the channel walls. But by removing these walls, the electrons are instead confined by a sort of magneto-electrostatic trap. As the electrons travel along the magnetic surfaces, they experience a large mirroring force, particularly in the center of the thruster where the magnetic field gradients are quite large. This mirroring for wall-less Hall thrusters has been shown in PIC simulations in a recent paper by Matyash. And I should note that this mirroring exists in Hall thruster too, but appears to be a larger factor here due to the larger gradients. Similar to conventional Hall thrusters, electrons are inhibited from moving towards the anode by the large magnetic fields, and so a local electric field is formed in the region of low mobility, and unmagnetized ions then accelerate along this electric field and generate a thrust. However, due to the strong axial component of the magnetic fields, the electric fields are quite radial, and the ions accelerate at large angles from the axis. This high plume divergence is a real problem for these types of Hall thrusters, as it not only leads to lower thrust and efficiencies, but presents a risk for spacecraft as the high energy ions may impact components. Another issue that has been raised with these thrusters is that without any channel, there is a risk of not ionizing all the propellant, just all leak out. However, recent measurements in a paper we just released, and this is a picture of our thruster where we have a cathode up here, and it's shooting to the right. This is just a probe in the way. So recent measurements, we showed that the propellant utilization can actually be quite high for these thrusters, even exceeding unity in some regimes where we think we're getting doubly ionized xenon right over here. But we found that the current utilization, which is the ion current over the discharge current, had relatively good efficiency, but still not very good. It still has some room for improvement there. But one thing we found quite surprising, we found very efficient acceleration of the ions. Because the magnetic field is large next to the anode, you would expect that the electric field develops near the anode and the acceleration region and the ionization region overlap. But when we applied 250 volts, we saw very high energy ions in the plume, up to about 90% of the applied voltage, which is a level similar to conventional Hall thrusters. So this was very encouraging. It suggested that with the high propellant utilization and the voltage utilization, we might be able to get efficiencies approaching that of conventional Hall thrusters, but the main roadblocks appear to be the not so great current utilization and the high plume divergence. So just to focus on the plume divergence a little, the trajectory of the ions is dependent on where the ions are produced and the potential profile. And the potential profile is not very inherently obvious for this thruster. It appears that the central region is critical. Recent measurements have shown very high plasma density in the central region. So to return to our little schematic, there appear to be two regions where the plasma concentrates, in a ring around the anode and a blob in the center. So the plot I'm going to show next is rotated compared to this picture, so I'm just going to rotate that. And you can see in our plasma density measurements, this is for a 6 SECM thrust mass flow. We get these two regions of high plasma density. So we expect a high plasma density above the anode. That's where the gas is coming out. But the region in the center can make some sense. I mean, we have this mirror confinement happening. So the plasma is, the electrons are trapped there, and the neutrals and the ions coming out of the anode make cross paths on each side and congregate there. But if the plasma density is high there, then we need to know where these ions are going. So they make a significant portion of the total plasma density. So if we're taking the equipotential assumption with our cathode outside the plume, we'd expect that this magnetic field line to be equipotential would have very low potentials in the center of the thruster, roughly the cathode potential. However, when we measured it, we did not see that at all. And this is a consistent result we saw over many measurements. We found that as we put our emissive probe along this axis, we saw this very high rise in plasma potential. We applied 250 volts, so the plasma potential was approaching the applied anode voltage in the center of the thruster. So this is quite significant because not only does it mean the equipotential assumption does not apply in the middle of this thruster, the ions of the center also have an acceleration region and of a mechanism distinct from the acceleration region above the anode. And speaking of the anode acceleration region, I have it plotted right here. You can see that the central acceleration region is more downstream than that above the anode. So this is significant for two reasons. The first is that you can see we have quite large acceleration of the plume in the center, which has been measured in cylindrical Hall thrusters too, suggesting that the divergence is a big part of this, of the magnetic field. And the second point is that at any axial position, our central plasma potential is larger than our anode plasma potential, meaning we have an outward radial force, an outward electric field, sorry, which may be responsible for these outward bound ions and the high plume divergence. So the mechanism behind this central acceleration region and why this potential structure forms is a little unclear. Our measurements, we first thought it might be due to the plasma pressure, but our measurements show that it was too small by at least a factor of 3 to account for this electric field that forms. But we have suggested several mechanisms which may be responsible for this field, including formation of a sheath on the floating surface in the center, which is boron nitride, and magnetic mirror, which we currently think may be the dominant mechanism. More details on the mechanism and can be found in our recent Journal of Applied Physics paper. The central acceleration region appears in other Hall thrusters, I should mention. We have measured it in the cylindrical Hall thruster to a smaller extent with both laser-induced fluorescence as well as probes. and in annual Hall thrusters to a smaller extent still. And our current thinking is that as thrusters are miniaturized, the magnetic field divergence has become larger, and so these effects become quite important to miniature plasma propulsion devices. So to reiterate, a high potential field forms in the center, which leads to high radial electric fields, which accelerates ions in these two regions, radially outward and leads to the high plume divergence. So we wanted to understand if we could reduce this plume divergence. And a method used for annual Hall thrusters was the implementation of segmented electrodes, as pictured here in the our sketch. They're put downstream along the channel for this paper, particularly near the exit. And the intention behind these segmented electrodes is to shape the potential profile in the channel and alter the ion trajectories. The semi-conical plume angle in this annual Hall thruster was reduced by about 4 to 5 degrees by this method. And I should mention this is for annual Hall thrusters, although there was an associated increase in discharge currents. So we wanted to see the effect on wall-less Hall thrusters to see if there's a favorable trade-off between input power and thrust. And to do this, we placed an electrode along the outer edge of the thrust, as shown here in the sketch, which we biased positively compared to the cathode. So without biasing the electrode, this is a typical current trace where the blue is the anode current, and the orange is the current of the electrode, which is just, a little around 0. It was floating in this case. And we see a typical breathing mode. It's very typical in this thruster, particularly in the regime we're looking at. However, as we increase the electrode bias, the outer electrode current increased, the anode current decreased, which makes some sense. We're diverting the plasma towards the outer electrode. What was very surprising, though, is we saw this the breathing mode amplitude greatly decrease. And this was a result we saw in nearly every regime, in every regime we tried, I should say. No matter if we started with high amplitude oscillations, small amplitude oscillations, the breathing mode appeared to be suppressed when we put about 80 volts towards the outer electrode. And this is quite advantageous because the breathing mode can be hard on power supplies. And these oscillations are typically filtered out with additional circuitry. And there may be a simplification for CubeSat power processing units, but it does require another voltage line for the electrode. So as always, there's a trade-off. And since the current is increasing in this electrode and the electrode is much closer to the cathode, we thought we would be increasing the total power by essentially creating a fancy electron heating device. However, we found that the total power decreased over all the regimes we tried. This appears to be due to the fact that while the total current in the system is increasing at high electrode biases, a large portion is diverted from the high voltage anode to the low voltage outer electrode, which lowers the total power by roughly 20% in some cases. So this is great. We're by using this electrode, we're lowering the input power, but I'm getting near the end of the PhD. I'm used to the idea of no free lunch in my experiments. So I figured low power, well, we must be lowering the propellant utilization, lowering the thrust. So we put on the thrust stand and thrust increased. So this was great. This is what we were originally wanting to see. We're hoping to see the plume get more focused and the thrust go up. But this, low power, high thrust means that the efficiency goes up. And now already the Wallace thrust we're working is very unoptimized. It started off about 16% efficiency in the regimes we're looking at. And it went up by this method to about 22%. So this was good. We also submitted a paper on this topic, which has a lot more information on the suppression of the breathing mode and these details, if you're interested. So our initial hypothesis was that the thrust would increase due to some narrowing of the plume by altering the trajectory of the ions. So we wanted to see if that was happening. And our measurements of the plume showed that indeed the plume was becoming more focused. In this case, the orange is the floating when the outer electrode is unbiased, and the blue is when it is biased to about 100 volts from the cathode. And you can see that the ion current on axis in the centrally increases, and off axis around the wings, it decreases. So it is becoming more focused. And if you look at the comparative actual portions of the ion currents, we see about an 8% increase in the expected thrust, which is roughly what we see in the thrust measurements. So this focusing appears to account for that increase in thrust. So to wrap it all up, it appears the use of the segmented electrodes in the Wallace Hall thruster suppresses the breathing mode instability, lowers the input power for the thruster, and improves the thrust. So this results in a thruster with higher efficiency, with a quieter operation. And the focusing of the plume was similar to what was observed in an annular Hall thruster, which suggests the use of segmented electrodes may be a general mechanism for such devices to improve performance. However, there's still a fair amount of work to do to work out what is happening in the thruster. We know the plume is becoming more focused, but we aren't sure why. I'm sure we are increasing the plasma potential along the outer edge of the electrode, but we don't know what's happening to the potential profile around inside of the plasma. This is because where we have measured the potential, we've seen that the magnetic field lines don't appear to be equipotential. But the use of the segmented electrodes in Wallace Hall thrusters does appear to greatly enable the practicality of these devices for CubeSats. The reduction in power requirements and the increase in thrust makes it a good candidate for use in small satellites, we think, particularly because the plume does become more focused, which lowers any risk of damaging any components. We're still looking to improve the performance further. This is very initial studies, but it already appears to be a fantastic method to improve these small thrusters. And I would just like to thank the United States Department of Energy for funding this work, and thank you for listening, and I'd be happy to answer any questions.
Thanks a lot, Jacob, for this very interesting paper. For me, of course, my team, but not only, probably.
Yeah, we think the magnetic nozzle is probably happening in the center, some sort of effective electric field.
That's really great. Just a quick question. What was the energy, the power level of your thruster?
Oh, right. So for these measurements, the blue line is about 150 watts, and the orange line is about 200 or so, 230, I think.
So we are still.
We also did 100 watts, but
okay.
It was very unstable. Actually, it was so unstable it only worked when we applied the outer electrode because it suppressed the instabilities. But I haven't shown it here.
Yeah. So when we look at the number of the although you managed to improve it, we are still far behind the annular out channel at this power level, around 50%. So this is still. But reducing the divergence is also very important, as you mentioned at the beginning, to limit interaction with the spacecraft.
Sure.
Sure. So, any question from the audience? I expected a question from Burak. No.
There is a question, I think, from Laurent. And
Yeah.
Ben.
Yeah, and Ben.
Yeah, but I'm not sure if it is for this session or for the.
Yes.
Ah, okay, Laurent.
Yeah. No, I was wondering about the neutral injection. I mean, how do you inject your neutral thing?
Sure. They go through the anode. So in our sketch, they're coming right out of here.
So you, it's. I mean, you inject. It's. Yeah, we in a vertical. I mean.
Yes.
Yes.
So yeah, coming straight up. We're using our existing anode from the cylindrical Hall thruster. It's a typical Hall thruster anode.
Okay. So okay. So it's through the anode. Okay. The same.
Yeah.
Okay. So okay.
Just quite strange because normally.
Yeah, I would say that maybe you have to to reverse a bit. Just to in a vertical. Maybe it could be just for, I don't know, just for.
Yeah, we've thought about different anode injection mechanism schemes, but we're still working on all that.
Okay, you take a simple. Okay, thank you.
Thank you.
Ben?
Yeah, just a quick question. How strong a magnetic field are you able to generate?
So it changes quite a lot around the, I think I have an actual, where did I put my magnetic field? Density plot. Here we go. So in the center of a thruster, it is very high. Close to the wall, it gets as high as 3 kilogauss, and then it drops off quite rapidly. Close to the anode, it's more on the order of kilogauss or so, probably a bit less, also dropping off quite rapidly. I have plots showing all that information in the paper if you want to get more specific numbers.
Да. О, Марьян,
This paper in particular.
Да, он сегодня в 8 должен быть. Я сейчас еду.
кто этот?
I had a
Okay.
quick follow-on question.
Andre, we can hear you.
Sure.
No, I switched off the microphone.
What current densities are you getting? Maybe I'm not sure how you define, I guess just across the entire exit area averaged.
You mean we were measuring in the plume?
No, kind of at the exit plane. Yeah,
Hard to define the exit plane in this case.
best guess, I guess. Maybe middle of the acceleration zone or at right end of the average acceleration zones.
Right. So I guess you could work it out based off the plasma density, and we do have electron temperature measurements. But let me think. I'm trying to remember what that was. We put in a planar probe inwards, but I can't quite remember that number. But I can get back to you if you need it.
Oh yeah, I'm just curious. Thank you.
Sorry.
Okay,
Yeah.
thanks, Ben. We have a question from Christophe Coppel.
Yes, thank you for your presentation. I was wondering about the cathode, where it is, and did you investigate on the effect of the cathode location?
Sure. So the cathode this is the picture of a thruster operating. The cathode is right up here. It's a commercial hollow cathode. So it's a little bit above, a little bit downstream of the face.
But did you change the position, or?
We have not, and I see where you're going. I think the cathode position does definitely change it, and that's a well-documented thing. But we haven't changed it for this. We still have a lot of work to do to optimize this thing.
Okay.
Thank you.
We have a question from Burak.
Hi, Stefan again.
Hi.
Thank you for presentation, Jacob. I mean, in general, what I think this external discharge, or as we call whole thruster concept, it doesn't receive the attention it deserves, because I mean, it brings lots of advantages. Like 1 kilowatt whole thrust, 2 kilowatt, you can bring its dry weight from 6 kilogram to under 1 kilogram, because basically nothing. But still, I don't understand why it doesn't receive the attention it deserves. So what's the next step? Is there any other project you will continue to this research?
Yeah, so I completely agree with you that this it's a very promising concept, and I think the biggest issue has to be this plume divergence. I mean, conventional whole thrusters get what, 30 degrees, and we're sitting at 60. So it's
I'm confident that that's really not a problem. That can be improved with some ideas, as you suggest. One is segmented. I thought there are some other ideas. That's not the problem itself. It's just I needed some dedicated projects to this concept itself.
Sure. So we're still working on this. I haven't graduated yet, but so we're still hoping to. I think if we show high enough efficiencies, and we may generate more interest in this thing, because typically when the previous all thrusters, and I don't think I saw ion energy measurements in your work, but Stefan's work, I think you were getting around 60% ion energy. And I think you were seeing about 50 to 80% propellant utilization in the XPT and the Walls Hall thruster. So already I think we can show it can be higher. So hopefully maybe everyone here will.
Is there any interest in the US, the market? Because what I show is 25% efficiency around 250 watt, which is quite enough to be commercialized. I mean, and it was just the first prototype. It wasn't optimized at all. And you're using segmented electrode to smooth the discharge oscillations. And I showed just using a uneven and homogeneous propellant injection, we can get almost DC discharge. If you look at the pulse, it's almost DC at 10 ccm, 15 ccm, and without using any damping circuit. Like,
Sure.
So I believe it's already good enough. 25%, 250 watts. I mean, the state of the art is over 40%. So, what is there any target that you target, like 35?
I mean, I don't have a company, so I can't quite.
Yeah, but you joining this conference, I mean, what's the US thing? The interest?
I mean, we've seen many companies making roughly 150 watt thrusters. I think at IEPC, we saw some companies saying they have 30 or 40% efficiency for a more conventional Hall thruster design. I'm trying to remember the name of the company, but so we have to at least beat that. I mean, we can offer higher lifetime, but a lot of these small sats they're not lifetime limited. I mean, sure, we have ambitions for deep space, but no one's doing it yet. So why have a high lifetime?
Jacob, I would say that we still have to demonstrate that we have a longer lifetime.
Yes, that is a very important point. Yes.
I also strongly believe, and this is the reason why we developed this, but it has to be demonstrated.
Yes.
Okay.
Yeah.
Okay, thank you.
Well,
Joach, we have a last question from Victor. No.
Me? Stefan, you're talking to me or someone else?
I was talking to Victor the song from Onera, but maybe I made a mistake.
All right.
He had a hand up, but no, it's not responding. Okay, so this will conclude your paper, Jacob. Thanks a lot.
Sure. Thank you.
Talk. Okay, so this paper was the last paper of this afternoon session. I would like to thank again all the speakers of this afternoon, Alfio, Benjamin, André, and Jacob, for a very interesting presentation. So now we will have a short break, a 20-minute breaks, and we will meet again at 4 p.m. for the roundtable that will be the final event of this conference. So I see you guys at 4 p.m. after having the coffee and the croissant and the cake and whatever you want, or maybe a soup, depending on the time. Okay, I see you in 20 minutes.
Okay. Stéphane?
Ouais.
Ouais, tu m'entends? Je t'ai envoyé les.
Je l'ai vu, il faut que je regarde.
Ouais, regarde, j'ai pas encore mis la conclusion de la table ronde. Peut-être quelques mots sur la table ronde techno. Je sais pas si déjà tu peux anticiper 2-3 trucs. Ouais, voilà, bon, je fais un truc très bref. Je vais pas.
Oh, je pense que ça peut être assez court. Hein.
Bah oui, non, j'ai un slide.
Les collègues, je peux démarrer la table ronde en présentant chaque acteur avec.
Oui, tout à fait.
C'est ce que tu fais ça, exactement.
Voilà, donc je voulais donc démarrer, je présente chaque personne.
Ouais. Après, est-ce que tu as prévu quelques sous-thèmes ou tu laisses complètement?
Ouais, j'ai prévu, j'ai repris un peu les suggestions de Stéphane et j'ai prévu 3-4 sous-thèmes.
D'accord. Ouais, et tu prends en gros un petit quart d'heure pour présenter les personnes et puis un quart d'heure pour le sous-thème. Voilà. En
exactement.
gros, ouais.
Un peu le sous-thème, je lance le truc, après je fais attention que…
Ouais, un quart d'heure par voilà. Et...
Ce qui va être compliqué parce que vous êtes nombreux.
Ouais.
C'est que tout le monde parle.
Et voilà, exactement.
Donc il faut que les présentations soient brèves, quoi, des personnes. Bon, voilà, qu'est-ce qu'ils font en 2 mots, quoi. Parce
oui, je cherche d'aller vite.
On n'est pas là pour avoir le CV de tel ou tel. Parce que, bon,
non, j'ai pris 2-3 lignes chacun.
Voilà, ça c'est ça. Et c'est même peut-être mieux si toi qui l'ai dit, parce que je sais pas.
Ouais,
c'est mieux. Ouais, comme ça, tu vas aller. Ouais, voilà, exactement. Parce que si commence à se présenter, ça peut être un peu long. Tu as raison.
Francesco a fait ça hier et c'était bien.
Ouais. Bah, à la fin, Francesco, on a fini à 2, puisqu'en fait, il y avait que les modèles, il me posait les questions, mais je lui répondais. C'était un peu. Bon, je n'ai pas anticipé ça. Ouais, en fait, c'était un peu. Bon, mais c'était bien. On était 6 ou 7, ça a bien duré 1 heure. Hein. Donc, tu vois.
Ouais.
Donc, ouais.
Ah, ouais, c'est ça, bien sûr.
Alberto.
Juste une chose pour démarrer, je peux donc poser le premier thème.
Je te passe en animateur.
Ouais, merci.
C'est toi qui vas animer.
Pour démarrer, je pose.
J'ai passé la main.
Je pensais poser le premier thème, après je donne la parole à une des 8 acteurs.
C'est ça.
Voilà, et après, voilà.
Okay. Bon, peut-être qu'à la fin, ils auront moins de choses à dire. Enfin, le dernier aura moins de choses à dire que le premier, mais bon, quoique, pas sûr. Chacun veut mettre ça.
Il y a des gens qui sont habitués à parler.
Ouais.
Oui, j'imagine.
Donc, non, c'est un peu nombreux, mais je pense que c'est bien qu'on.
Bon, mais de toute façon, on a un peu de temps aussi.
À peu près tous les, on a presque tous.
Parce que franchement, la clause, comme on disait, Alberto, on discutait avec Stéphane, la closure, la truc de clôture, ça va pas durer 40 minutes. Hein.
Non, c'est 5 minutes. Hein.
Ouais,
Oui, oui.
un slide, voilà, remercier à tout le monde.
Ouais, on remercie.
Bien sûr.
Voilà, c'est tout. Non, c'est pas le but. Voilà. Bon, le but, c'est plus pour poser les bases la prochaine fois, quoi. Où est-ce que, voilà, que les candidatures émergent, quoi. Et pour rappeler qu'on aura les vidéos encore sur le site, etc., sur YouTube, les gens qui veulent le voir. Voilà.
Bah, rappelle qu'on enverra un email à propos de l'agreement.
Ah oui, ça, oui. Ouais. Tu le mets, je t'ai envoyé, tu peux y mettre.
D'accord, je vais le rajouter.
Bon,
on fera ça la semaine prochaine.
Oui, pour l'email.
Il faut qu'on ait l'accord de tout le monde.
Oui, c'est vrai. Oui, parce que sinon on peut couper. Par contre, hier, j'ai bien vérifié parce que c'est vrai que le premier jour, c'était en direct, nous avait dit Antoine, là, Blancher, sur YouTube, mais ça veut dire que les gens, ils n'avaient pas besoin de payer pour suivre le truc.
Ouais.
Non, par contre, hier, j'ai regardé, ça ne marchait pas, quoi.
Bon, ok.
Hier, je sais pas. Et ouais, parce que sinon, il n'y a plus besoin de payer pour. Bon, c'est pas grave. Et oui, c'est offert à tout le monde, quoi. Donc, c'était un peu.
Allez.
Et ouais, donc elle avait fait. Mais ça ne savait pas. En fait.
Qui paye.
Marlène ne savait pas. Et passait pas du tout. Et si, ça marche en direct, je le fais. Voilà. Donc, ok.
Oui, parce que j'ai vu passer sur LinkedIn un message d'impulsion avec.
Ah ouais, d'accord.
Tony qui a mis ça. Voilà.
Donc en fait, il avait
Alexander Ariette et il disait il y a une diffusion en direct.
Ah, tu vois.
C'est possible ça.
Ouais, mais là, il a fait hier, ça, quand j'y suis connecté, ça marchait bon. Je sais pas, maintenant à voir. Quoi. Bon, on fait un petit break quand même, hein.
Ouais, puis je te regarde ton.
Ouais, voilà, ok. À tout de suite alors.
Tout de suite.
Hello, good afternoon.
Good afternoon.
Hello.
Hello.
Hello, good afternoon.
Hello.
Good afternoon, Davina.
How are you doing?
Good, thanks.
The sun is shining over there, I guess.
Yes, today in Rome, it's like the 15th of August. It's really hot.
I heard I had a meeting this morning with Rome. So
every time you
yeah.
come, we can have a coffee whenever you come.
Thank you. Could escape from raining Holland.
There's a big number of Italians in this call.
Yes.
Can confirm.
Spread all over Europe, but a lot of Italians.
Ciao Alberto.
Ciao.
Piacere, Alberto.
So we can start in 2 or 3 minutes.
Alberto, je pense que tu dois transférer Paul.
Yeah, it's done.
OK.
C'est fait. Alexandre.
And Alexander, yeah.
Alexander
is in the list, but you have to transfer.
Yes. Okay.
Sarah also, no, maybe.
Okay, Alexander, it's in the panelist.
Salut, Luc.
Salut. Ah,
hello, good afternoon.
Hello.
Alberto.
Hi, Alexander.
Hello.
Thanks for helping me with the technical things. Short notice.
So. It's a job.
Let me try to put the video up as well. Can you see me?
Yeah.
Perfect.
Yes.
Alberto, Sarah Correro is also in the spectator.
Yes. Yes, I move also.
Is it Sarah or Mick?
Mick.
Talk for Iana, it's Mick.
It's Mick. I also move. Okay. Okay. I think that everybody. Okay, all the people are here, I think. So we can start this roundtable. I'm very happy to moderate this roundtable, a very, very high-level roundtable. The topic today is obviously the micropropulsion, but especially the new trends and new technology and new opportunities in the field of micropropulsion. We have, with respect to yesterday, it's a very technology-oriented roundtable. We have 8 actors. I propose that I present each participant with some words about each person and the role of this person, and then I start with the topic, and I let you speak about this. So around this round table, we have Davina Di Cara from ESA, Paula Combe from ExoTrail, Giulio Corral from Trust Me, Alexandre Reiner from Impulsion, Luc Herrero from Comat, Louis de Gouillon-Matignon from Gamma Space, Mick Viner, sorry from the pronunciation, from Yenai Space, and Fabiana Milza from T4I. So Mick Vienen from Yenai Space, the co-founder and CTO of Yenai, he obtained a master's degree in space engineering and at the TU Delft in the Netherlands, currently finishing a PhD thesis at University Carlos III de Madrid on the topic of diagnostic for electric propulsion devices. And he is the co-founder and the CTO of Yenai Space. Fabiana Milza from T4I, she's marketing and sales manager. Fabiana holds a master's degree in astronautical engineering from Sapienza University in Rome, where she performed a research on innovative materials for human life on Mars. She won the Global Awards at NASA Space Apps 2016 and started her entrepreneurship experience in the downstream sector. She joined the T4I in 2020, and her role is marketing and sales manager. Paula Combe from ExoTrail, CSO and co-founder. After his studies in aerospace engineering, Paul co-founded ExoTrail in 2017. Since then, he holds the position of Chief Scientific Officer. He challenges all the technical development in the company, from electric propulsion solution to operation software and in-orbit services, with a strong strategic mindset. Luc Herrero from Comat, the innovation officer. Born in France in 1981, he graduated from Arts et Métiers Paris Tech, Superior Toulouse, and as a master in physics. Luc joined Comat teams as propulsion lead engineer after 7 years at Airbus Defence Space. He joined Comat in 2012 to develop in-house products for new space market. He's now responsible of business unit product for small satellite. Davina Di Cara from ESA, electric propulsion engineer. Davina Di Cara holds a degree in aerospace engineering from Politecnico di Torino, as me. She joined ESA as electric propulsion engineer in 2004. She has been involved in various ESA projects, currently working on Galileo second generation project, and she has managed several R&D activities on electric propulsion technology. She's the focal point for all R&D activities related to electric propulsion for navigation, CubeSat, et ESA. So Alexander Reiner, the Impulsion CEO and founder. Alexander is aerospace engineer and founder and CEO of Impulsion. He holds a master's degree in physics and PhD degree in aerospace engineering. Alexander started his career in the space industry with Ruach Space. Later joined the Austrian Institute of Technology and became the team leader for electric propulsion system. In 2013, he became the head of the Department of Aerospace Engineering at FOTEC, the research subsidiary of the University of Applied Science, Wiener Neustadt. And after that, he founded Impulsion in 2016. After that, we have Giulio Corral from Trust Me, electric propulsion researcher. Giulio Corral, 28 years old, PhD in aeronautics and astronomics from University of Tokyo. After 5 years of research at JAXA, the Japan Aerospace Exploration Agency, in the electric propulsion laboratory, he joined Trust Me as a space propulsion engineer, leading several R&D projects aimed at delivering next-generation propulsion system for sustainable space exploration. And then we have around the table Louis de Gouillon-Matignon from Gamma Space, the CEO of Gamma Space. Louis, 29 years old, PhD in space law, La Sorbonne University and Georgetown University. CEO of Gamma, a French startup aiming at revolutionizing deep space access thanks to solar sails. So now we can start the roundtable. I propose a first question, a first topic about the evolution of the size of CubeSat, microsat. Today, what is your vision on the size of CubeSat or microsat? And if we have to increase or not the power and the size and the volume with respect to the electric propulsion. What is your vision with respect to the size, the power of the platform today and the electric propulsion capability? So maybe I suggest that we can start from, for example, from Alexander, from MPCS, and then we change the person. Maybe.
Sorry, yeah. Can you hear me?
Yes.
Okay. Well, first of all, thanks to Stefan for putting this together. It's really great to see all of you again, even if it's virtually. It's always a pleasure. Alberto, thanks for hosting it and for having me on the discussion.
Thank you.
So we, my personal view and my view on from us supplying a rather large range of CubeSats and microsatellite platform is that the trend is clearly going towards larger and larger platforms in all domains that I'm seeing. So CubeSats are growing, you know, from 2 to 6U, from 6 to 12U, you know, and so to say gradually kind of growing. What used to be a 100-kilogram satellite is now a 150-kilogram satellite. Within a few years, kind of everything is in my mind a little bit shifting, you know, to the larger end of the spectrum. That does not mean that there is not new applications for the very small CubeSats. So we see new proposals, you know, coming up with, you know, small CubeSats all the time. But as the maturity or the general trend in the industry is towards, it's kind of a convergence towards more, you know, higher capabilities, also higher demands in mission assurance. That is flowing down from the insurances, of course, you know, where you really need to have mission success at some point through primes that are consolidating a little bit, you know, between the new space and heritage space domains. In general, that adds, you know, complexity and mass, I would say, to the systems. However, we are not the ones, you know, the smallest ones on the market in terms of propulsion. We are supplying some 3U, you know, but very specific applications. So there is smaller, you know, propulsion systems dedicated for that, that maybe have a better view on the very small end. But from what we see, supplying between like more like in the 6 to 12U side towards 150 kilograms, you know, using multiple thrusters. I see in general a trend, you know, into being larger, more demands on mission assurance, reliability, and so on.
Okay, very, very interesting, Alexander. And what is the opinion about this of ESA, Davina?
First of all, thanks again also from my side, Alberto, to set up this together. I concur, in fact, with what Alexander say, and when we ran the market analysis together with Euroconsult, in fact, for our harmonization process, we asked the question, because our harmonization dossier has set up a limit up to 16U, but we did ask the question, what should we already start considering at least the 50-kilogram satellite? And it turns out that actually there is quite a trend there. And at the moment, we at ESA, we put this this limit at 16U, considering all the propulsion system for CubeSat, the one to be employed on 16U. But definitely, we see a trend at least to go up to 50 kilogram. With the use of the same kind of propulsion system. And this is a very good trend for us, for EP, because of course bigger becomes more opportunity for EP, because of course there will be more power available, and so this is actually a trend I can confirm.
Okay, thank you very much. And what is the opinion of ExoTrail about this?
Thanks, Alberto. So it's what Alexander said. So we really see that there is an acceleration in all the market segments, meaning that you still have a lot of 3U CubeSats, 6U CubeSats, and bigger. At ExoTrail, we are targeting satellites from 10 kilograms, so 6U, up to 250 kilograms. And we really see that there is a push for accessible satellites in the 50 to 100 kilogram range. It used to be satellites used for science or dedicated missions. Now it is made for constellations. We really think the value of the market of electric propulsion for us is around this 50 to 100 kilograms and higher.
Okay, and also with respect to little or medium constellation today, do you see some change with respect to the size with respect to constellation or not?
So the size of the satellites.
Yes.
So yeah, so I mean, when there was quite a lot of factor at the end of the 2010s. We're targeting 3U or 6U. Now the majority of new actors are targeting bigger satellites, and so you still have those looking for very small satellites, which are here, and that start to have a real commercialization of the service. On the other end, you have a lot of new commerce coming to bigger satellites. So there is a market for, I think, from 3 units to bigger than that. I think we're getting a little bit more than 3 units. But there is a clear trend that more constellations are towards 50 kilogram, and there's less constellation that's entered the market now on very small platforms.
Okay, thank you, Paul. And I'd like to know the opinion about this with respect to the technology that it's a little bit different from gamma space, for example, that use another type of technology than other actors here around the table. So I'd like to know their opinion also.
Thanks a lot, Alberto. So very happy to be among you guys. I'm not a scientific guy. I did my PhD in law, so I'll be more helpful on all the legal and policy aspects. Well, I think that the thing is, at Gamma, we're not really looking at low Earth orbit, or we're not looking at anything that is in between the Earth and Moon. We're actually looking at beyond the Earth-Moon system, and for now, only a few CubeSats have been launched beyond the Moon, especially the Marco satellites that were developed by GPL. There are a few satellites that are going to be launched. Most of them are 6Us or 12Us. They'll be flying on Artemis 1 in November. And those CubeSats will be some demonstrators in deep space. Concerning LEO, what I'm seeing from launchers is that we have less and less small satellites. I mean, 3U standards or maybe even 6U standards, and more bigger satellites. And that's what has just been said. I don't know for deep space. It would be amazing to, just see a flotillas of, I don't know, thousands of CubeSats flying in deep space to do low-cost exploration missions. And I believe that there's a place for that type of missions. I mean, the Marco satellites were great. They were accompanying a mother mission towards Mars. Some missions are going to fly again in November. They'll do asteroid characterization. They'll do lunar flybys. So maybe the, revolution using small nanosats, especially 6Us and 12Us, that happen in low Earth orbit for the past 10 years will happen in deep space in the next 10 years. And then maybe again, we'll see the movement of having bigger and bigger satellites, but that's for sure. I don't see like 1U CubeSats and 3U CubeSats flying in LEO in the upcoming years. But actually, we're trying to develop our technology of solar sailing around nanosats for deep space. We believe that other types of propulsions, especially electric propulsion, a fortiori chemical propulsion, are maybe a little limited for long, like duration missions. I don't know, but that's what we're working at the moment on. I hope it was clear, but I believe in nanosats for deep space in the upcoming future.
So yes, thank you very much. Yes, I'd like I have another question after about this subject, but now I'd like also to know the opinion of Fabiana from T4I on the subject.
Thank you for the introduction before. I agree with all the colleagues that spoke before. Regarding the CubeSats, I'm pretty sure that the 612U size will be the most chosen. Regarding our propulsion system, for example, we didn't perform the IOD in a standard CubeSat, but we are in a CubeSat carrier that is already in the 32 kilos. So it's in the bigger size of the nanosats and microsats. What I see from my experience from prospects or clients that come to us asking for propulsion systems, because we have both electrical and chemical propulsion systems, is in the 112 kilograms platforms, even for constellations. The thing I see the most is that constellations that are in CubeSat size, like 3Us, they don't ask for propulsion. They prefer to send hundreds, thousands of CubeSats, but without propulsion. Instead, when someone is planning to have a constellation in the 100, 200 kilograms, they really need propulsion. So it's a completely different story. But another trend I see is more in a CubeSat carrier or space tugs. I guess, in my opinion, that will be the trend, the biggest trend in the future.
Thank you. Thank you very much, Fabiana. And for Comat, Luc, do you have the same vision than T4I, for example?
Okay. For Comat, we have defined 3 segments to target our project. Okay, and we have almost same vision as a participant. We have the first segment with 3U to 6U. We target exactly this segment for science applications with a better trade-off between quality and cost. We have very low-cost satellite, and we can do science with low cost. And we have another segment with a lot of demands on the market. It's radio frequency missions with 12 to 16 new satellites. And this segment is very pushy today. We have a lot of asks for commercial mission with high reliability, with life duration of more than 8 years. And this segment for us is very important, very special, because I think it's a coming year market for us, with more reliability and very tricky qualification and evolve for this kind of mission. And we try to go another segment, which is an optical satellite mission with 50 kilogram satellites. And this segment needs more capability for thruster, of course, but there is a lot of constellation right now with optical segments, with optical capabilities in this class of satellites, about 50 kilogram. For us, we have only 3 segments with a dedicated mission that we target, and at each segment we have a clear different specification, different cost, and different quality requirements.
Okay, thank you, Luc. And Mick from United States, can you give us also your point of view?
Yes, first of all, thank you. I'm very happy to be here and to join you all in this conversation. We are aware of the trends that have already been mentioned, like some users or customers are going to larger satellites, but I think there's also opposite trends. Alba Orbital just got funding for 1,000 pocket sets, which are even much smaller than the CubeSats we're talking about. SpaceX recently acquired Swarm, which are, I think, 1/4 of a U. And they actually, I think they do have enough propulsion. It's a registered jet, but still. So there is also it ran in the opposite direction. And I think, for instance, the other thing is that many of the electrical systems available take up 1 or 1.5 U around 50 watt or more. So of course, if that is what is on the market, no 3U is going to want to buy a propulsion system, because if it takes up half their satellite, then that's not really, there is nothing available for them. So that's, for instance, what we at ANI tried to do, is actually to make thrusters even smaller and efficient at lower powers to fill that niche. And so I think until there is solutions available for these power ranges and these volume ranges, it's very much the question if people want propulsion or not. Because if you can make it fit in terms of power and volume and mass, and you assure the reliability and it works, and you take away all the pain points that propulsion can have for the customer, why would they not want it, regardless of the size of their platform?
Yes. Thank you. And Giulio, the trust me vision is the same?
Yeah, so I mean, many of the points have been mentioned by all my colleagues here as well. So for how we see this, it's likely that the standard constellation size satellite is going to be in the 100 something kilograms that were mentioned before. These are those that are more likely to require sophisticated propulsion and more likely to be deployed in a large scale. Like, when you talk to constellation customer who wants this constellation to become revenue generating, for, I mean, there's many observation and whatever else that want to work in this scale. Those are probably the most interesting from the point of view of like our community, the propulsion community. But it's not like smaller scales would say the market there is still somewhat oriented on these super small, like 3U or little more, some of which still already need propulsion capabilities. So we see opportunity there as well. We expect that market to stay, of course, in the field of technology demonstrations, universities. So maybe require, in some cases, we've seen even these 3Us requiring a bit of propulsion capabilities. But of course, where there's probably going to be growth in scale, it's once all of these 100-ish kilograms satellite constellation will start being deployed and will need substantial propulsion capability.
Okay, thank you. Thank you very much, Giulio. And so I'd like to start from the answer of Luis on the exploration subject. So I have a question on this also to other actors. It's very interesting that we have here Gamma State that works on exploration propulsion. So today, what is your vision about the place of CubeSat and especially the propulsion for interplanetary scientific ambitious mission and exploration? So I'd like to know if you think about this application for electric propulsion. So maybe Giulio, can you give me your opinion about this?
Yes. So as well, so the things we cannot discuss too much in detail because there's nothing public, but there is definitely a place for products like a small propulsion system for this kind of missions, like beyond, say, just the Earth orbit, can be interplanetary, can be lunar, can be whatever else. The thing that needs to be seen is what scale makes sense, because of course, super small scale, we see the value of the science that you can get out of it may be reduced. But this, of course, so it's going to depend a lot on what other fields of space engineering develop. If technology on observation or scientific instruments improves a lot to the point that 3U CubeSat becomes capable of doing high quality science, then you will see a storm of these scale CubeSats. But so far we've seen somewhat larger satellites interested in this sort of missions.
Okay, thank you very much. And a question for Paul, because yesterday I read on LinkedIn that Exotrail will work on a lunar mission. So Paul, can you say something about this new topic?
Yeah, so actually there is, well, both in Europe and in the US, there is a really a new lunar area, let's say. So agencies really put money to run around the moon and to assist lunar activities. And so, yes.
Paul, we have some problem to hear you. I think that we lost Paul. So, okay, we can maybe
Alberto, I can follow up on that because I think we are in the same kind of ballpark here.
Yes.
On several of those missions. What I think Paul wanted to mention is that the agencies, both in the US as well in Europe, are currently, looking very much into this topic of, the cislunar activities, right? And yes, there is a place for CubeSats, both for scouting, a kind of precursor activities, but then also in potential, future infrastructure, be it inspections, be it communication networks and things like this, So yes, I think there is definitely a role for propulsion, in particular electric propulsion, because you need you need very high total impulses for such missions, right? And be very propellant efficient, and that typically is something that is where electric propulsion in general can answer very well to those kind of demands. However, the big issue that I see in these missions, and we are involved in several, but the big issue I see here is that really neither the agencies, sorry, Davina, but neither the agencies nor the primes who are working on these things have clear understandings and pictures on how they want to address such missions. So what I'm talking about, is I want to make a CubeSat mission, Marco, but then it costs 2 million, right? Because you add all the kind of overheads that you need for a Mars mission, right? Which is then not even sufficient to get to satisfy actually the requirements, but it's somewhere in between. And we see that throughout the course of several projects, that there is a constant kind of struggle, and it can be a very constructive struggle in the end, So I think these projects are very, very valuable. But in terms of the actual, outcome, it is currently in the market, the way I see it, not clear. What does it mean to have a small set or CubeSat mission going to the moon, to the Mars, or exploration, in this framework? Because the visions on that, on the requirements, reliability, and so on, are crazy, And then it depends really on who is in the reviews. You have triple redundancy on propulsion requested, and then you have a board computer which is COTS components next to it that drives it, and this, in concept, and that's kind of currently very, very interesting struggle that the industry has, I think.
Yes, and Davina, do you want to say something about this?
Yes, I understand the struggle, and to be honest, I also witness, but we have to keep in mind that those kind of missions are sort of special. I mean, the science mission, interplanetary mission are not everyday business. So they are a bit the Rolls Royce, the Ferrari of the mission. So yes, it's difficult to canalize them into the CubeSat world. Having said that, we do have a Margo, which is the first standalone CubeSat mission, because so far what has been done through carrier. So this will be the first time that really high delta V will be demonstrated. But of course, they are not the typical CubeSat chip mission, that's for sure. And reliability requirement will play a big role on and driving perhaps the cost to a higher level.
Okay, thank you, Davina. And so I come back to Louis. Louis, so I imagine that you have a real vision and a roadmap on this subject with respect to your technology. What do you think that your technology can give to the CubeSat exploration, CubeSat for exploration, for example?
Thanks a lot, Alberto. So there are lots of, I don't know, I've heard lots of things, and maybe a few answers of things I've thought about. First of all, when we say CubeSats, like Marco, costs in the millions, like, I don't know, 2 to 5, I believe the budget for the 2 Marco satellites was 15 million. So I believe it was around like 7 million each. With the launch, it's still very, very, very cheap compared to most of the deep space missions. I mean, usually a deep space mission is in hundreds of millions of dollars. So I believe a few $1,000,000 for the beginning is not that expensive. Of course, it's way more expensive than all the low Earth orbit missions, but still it's very cheap for deep space mission for true science. I also believe that the deep space area is still a very complicated area, since most of the actors are yet public agencies. But I believe we're going to witness the same revolution that happened in low Earth orbits. Like, I don't know, 20 or 30 years ago, we had a paradigm which was different. Most of space agencies were, launching satellites. We had a few commercial companies exploiting satellites in the geostationary belts. Then we had more and more like private companies, universities, and scientific laboratories launching in low Earth orbits. And this was made possible thanks to the large reduction in launch costs and cheaper and more standardized components. I believe this revolution will happen in deep space too. I mean, we're having the Starship that is being built at the moment, and that will fly. And that will be a tremendous change for the whole space industry. We have smaller and more modular and more standardized components for deep space. We have companies such as Sinclair Aerospace, which was just bought by Rocket Lab, developing its own Photon module. We have so many new contracts awarded each year by NASA to companies such as Astrobotic, Made in Space, Intuitive Machines. All those companies, they just live on public funding and on contracts awarded by NASA and other major agencies and actors of the space domain. So my belief and my feeling is that the trend is that we're going to go deeper and deeper in space, because that's just that's history's way of moving, and that's the sens de l'histoire, as we say it in French. And I believe there are going to be more and more missions in deep space. First of all, there will be more and more missions around the moon, because the moon will be a great infrastructure around the Earth for all the missions to fly, maybe towards Venus and even further. And then, of course, we'll have true in-space infrastructure with in-space manufacturing, with in-space refueling, with on-orbit services in low Earth orbit, and maybe even higher. But what I believe in regarding the subject of this conference is that nanosats are a great way, are great sentinels, are great, way of making science cheap. And we believe that we may see in the upcoming future, flotillas of, I don't know, 100, maybe thousands of nanosats, standardized nanosats doing science for cheap, I don't know, characterizing asteroids, doing Mars flybys. So small satellites may be, accompanying more major missions. That's what was doing with the Marco mission. And our project at Gamma is allowing free and infinite propulsion for those spacecraft. So we're actually now working on deploying the largest structures ever. We're having our first launch next year, July next year. We're launching in LEO, but just to test our deployment system. And we'll be flying a 110 square meter solar sail. And our project is to have a 400 square meter solar sail with a 12 view for our first deep space flight by 2024. We are targeting a Venus flyby, and we are at the moment discussing with many potential partners, especially CNES. And thanks, Alberto, for your help and for the different talk we have. And we want to show that with solar sailing, we can have a source of propulsion, like electric propulsion or chemical propulsion, that is infinite. Of course, it's not as strong, the thrust is not as strong as other types of propulsion, but it's still, when we have a big sail and a very small spacecraft, and we have an overall ratio of surface mass that is quite interesting, we can have great statistics. And for now, the first mission we're launching, we have a thrust of approximately 0.5 million Newton. So that's quite good, and our ISP is infinite, since we're always pushing thanks to the light present in the solar system. So, but my belief is that we're going to use more and more nanosats to do deep space surveys and do deep space missions, because it's a great and easy, cheap way, especially with launchers such as the Starship and maybe the Terran rocket from Relativity, and there's another rocket, the Electron rocket, that is in preparation by Rocket Lab. It's a trend, and we want to be there at the beginning.
So thank you, Louis. And Mick, I like to know if at the United Space, do you have also a vision on or a roadmap about exploration CubeSat market or not?
Sorry, for deep space, you mean?
Yes.
It's for us, it's very far off in the roadmap, I'd say. I do not see a particular problem against using CubeSats in deep space. It is much cheaper, as Louis already said. It also makes it more affordable to fail. And in the end, failure is what it's like a cheaper way to iterate and try things out, as you cannot fail with a 100 million satellite. If you have the propulsion system to get you there, then I'm sure that nanosatellites can just as well be used for deep space missions. Another thing is, instead of sending a larger satellite, you could, for instance, send swarms of smaller nanosatellites that together could solve or create better science, because I'm sure we said it before, nanosatellites cannot give you the same output in terms of science as a larger satellite, but a swarm, for instance, can. And that has, for instance, a certain redundancy, but at the same time, this would require propulsion. So for us, that would be a viable solution, perhaps.
Okay, thank you, Mick. And so very interesting topic. Thank you very much. So now I have another question. It's a very, I think it's a very difficult question, but I want to go in this direction now. So my question is, if have we reached the peak in terms of startup and technologies now, globally speaking? So maybe Fabiana, can you give us your opinion about this, about
if we reached a peak on the startup
yes, and technology also.
Okay, I come from the startup environment, okay?
Yes.
And I left it for a more established company. So I moved from a startup to an SME for a reason. So I have a really personal opinion on startup. I see that many startups in the space field are becoming real entities, real companies. I see that there is a financial problem, like you need private investors. At T4I, we don't have private investors. We are all bootstrapped. But it's really rare to have a company or a startup that didn't raise money but reached space. So I can understand all the difficulties for a company, just having contracts to have the internal funding to get the milestones in plan. So I must say that all the institutional sales or institutional opportunities are a big opportunities for all the companies, above all here in Europe and in the US. But I have a marketing point of view, and I would love to have more commercial opportunities regarding also the questions before that I didn't answer. I'm looking for a cislunar economy, not just a scientific or institutional opportunities. But I'm skeptical, like I don't think it will happen in the next 5 to 10 years, but it's a good goal for all of us, like to have a proper economy in this space, or at least around the moon. So private funding is the biggest choice for startups and companies. And we don't have so many investors in Europe. Like Europe is not US regarding private financing. So this is for sure.
Yes, sure. Thank you, Fabiana. And so always about this, Luc from Comata, I have a question for you. What was your goal when you choose vacuum arc thruster technology, for example, when you started at Comata?
Yes. At the beginning, our goal is to to transform propulsion very simpler. Okay, I work a long time at Airbus, and I have a look on each issue with propulsion as a tank or something like that, to have a high pressure tank, to have piping with titanium, something like that. And I would like to extract this technology from this constraint in ground or constraint in flight. Okay, so I go to what I think it's a simple technology. Okay, it's complex physics but simple technology, and I try to push this way to have a very compact and simple things that can be manipulated by everybody as a student or something like that. And moreover, which is important for us at the beginning, is to have a no constraint in flight, no heat ups, no thermal regulations, and something like that. Okay, that's why you choose this technology. We know that we have other constraints, of course, but we want to make a propulsion simpler with this kind of technology. This way that we work on the vacuum arc.
Okay, thank you, Luc. So for you, for example, it's simplicity, and I have a question for Davina today. What is your opinion about all the actors? So I think that in the CubeSat propulsion field, most of the actors choose simplicity. But do you think that we also have to choose performances versus simplicity, or what is your opinion about this?
Well, again, when we run the mapping in the status of the technology, we see that there are, as you say, several actors, several different technology at different stage of development, some of them flying, some of them yet in a research state. But I do think that there is space for differentiate them, because the applications are quite diverse. So there will be mission where, for example, simplicity and is the key requirement, but there will be other mission where, for example, high thrust is the must, because, for example, they will have to reach orbit or doing a transfer in a short time frame. So at the moment, we see quite different requirement coming from future missions. So we will not be in a position to say which one will be the best and where we should invest. For sure, what all of them will be perhaps face in the future is the need to demonstrate reliability. Need to demonstrate increased lifetime, because we see that most of these missions require a longer life in orbit. And one of the things that might change in the future will be linked to wherever the regulation on space debris mitigation will change for CubeSat or not. At the moment, the 30 years disposal in LEO, is benign for CubeSat, because most all of them will make it even without propulsion. But especially in LEO, as soon as the number will start increasing, then perhaps perhaps we will see more this requirement coming into place.
Okay, thank you, Davina. And Giulio, what is the vision of Trust Me about this, about the simplicity of a trust system versus performances?
It's definitely an interesting problem. So generally speaking, for what we've seen, customers tend to like simplicity. In general, they are very happy to buy a thruster in which it works literally by sending the command thrust and it's gonna thrust. But in the end, tend to buy performance. For what we've seen, customers, of course, all of them are gonna have different requirements. All of them will try to push them as high as possible. The ideal thruster will be 5 milliNewton, 10 kilonewton second, and whatever double lifetime tested. But they tend to adapt to, especially when say when the system engineer inside we are interacting with has a good idea of the mission they're gonna perform, whether they should choose Thrust or ISP or whatever else. They are able to do proper trade-offs in determining which propulsion system they want to use, or even within the same family of propulsion systems, which specs they'd rather operate it. For this reason, yes, simplicity generally well appreciated. Performance tends to, so there's always going to be demand for extra performances. And from the point of view we were discussing before, like whether we've reached a limit or not, I think there's margin. So with our technology, we see margin in different directions. We are planning relatively soon, we're going to offer things like increased total impulse, possibly increased thrust. Overall, the satellite users appear to like having this super compact thrusters, which have a very extended range of potential operating points and hence different performance they can get to.
Okay, thank you, Giulio. And Paul, do you think that very hard question? Do you think that the market today is big enough for all the technologies or not?
So clearly, the market is expanding. You have a lot of traction, and we answer to requests every day. I think you have propulsion systems which are very specialized. Some are very good to do station keeping, others are good for positioning. And I think that it will really depend on what the operator and the launch landscape will look like. So I really think that there is room for 2 or 3 technologies because you will always have some architectures that will have to be optimized. Then for others, it will really depend on who is mature enough at some point. So at the moment, there are not that many technologies which are mature enough to have an industrial scale. I think that when the 2 or 3 typical missions performed by propulsion will be covered, then it will be harder for new technologies to arrive, except if there is a real technological breakthrough involved.
Thank you, Paul. And Alexander, what is your vision about this? Do you think that is the place for all the technology or one technology or 2 technology we win all the market?
No, I think space will never be a winner-takes-all market, for sure. There is way too much national geographic interest in the overall space industry for that. No one wants single sources, and in the end of the day, if you follow all the chains back, it's still very much dominated, the space industry, by, globally speaking, by entities that have these kinds of interest to actually not allow for that. So I don't think it will ever be a winner-takes-all situation for that reason. Also, from a technological point of view, I think any specific technology, even if it's modular and versatile and so on, you can probably go up to like 70% of the applications, but certainly not one size fits all technical solution. Where does that bring us? Yes, I mean 2 or 3 technologies is a number you can probably relate to. But the question is what do you define as the cake? So is it, I think there is a niche for everyone, for sure, right? The question is, are we looking at the kind of majority of the commercial market? Then yes, I think there will be a few players who will be successful in demonstrating industrial capabilities, production capabilities. To be honest, I don't think simplicity is really the key driver here. It's a nice to have feature. Yeah, it's performance, reliability. Reliability for me is not the fit values, to be honest. This is one aspect, but it's also how resilient is it to is the system to being just mishandled, for example, right? I mean, with 87 thrusters in space, with 44 years of cumulative operation in space, but I can tell you, in all these missions, we've had situations where thrusters could not be used because the spacecraft had issues, and was just, it's hard to make a spacecraft move. It's not just the propulsion system. And at the end of the day, it's very rarely the way you send commands, the interface is, or the simplicity of the interface is to me not the driver. Yeah? But how much is the thruster itself capable to catch mistakes from operators, right? And not allow like harmful operations and all these kind of stuff. Yeah, prevent spacecraft charging under all circumstances in electric propulsion. That's a big topic, right? Things like that. So to answer your kind of question, I think there is room for everyone if you're kind of okay with a specialized niche. If you want to supply a large chunk of the kind of industrial market, I think there is, on both platform side, but also on propulsion, on the domain of kind of proposed propulsion solution, I would say there is currently, I feel it's oversaturated. Right.
Okay, thank you, Alexander. And Mick, what is the vision of the market today with respect to these for United Space?
I think Alexander already covered a few of the points I wanted to make. It really has to matter with the niche, like how do you define, if there's one of the same technology or two technologies that have, for instance, the similar performance, but one is much easier to integrate, in that case, the better one will be chosen and outcompete the other one, perhaps, but only in that niche, maybe not on the larger or in a different niche or on the larger scale. So I think it will be a combination of different technologies and multiple companies that will service the whole market. And I also think that the market will change rapidly over the years because new technologies are being available, different solutions, different niches can now have propulsion. So that will create new opportunities, and the market will also change in response to the technologies that will become available over time. And so what the market will look like in 5 years or in 10 years might be very different. But I think the answer in general is yes, I think that it's large enough for multiple technologies and multiple companies. But which ones and how this will change over time, of course, that's a large question.
Okay, thank you very much, Mick. So yes, and Fabiana, for T4I also the vision is the same about the market and
partially, like I agree with the thing that there's room for everyone, above all if everyone finds the perfect niche. So it's not just to find one niche like the most suitable, but I guess that this conversation is a little bit biased because we are almost all electric propulsion providers and we are missing a big part that is also chemical propulsion. So if you ask me, there will be only one or two technology. No, because there's also all the chemical parts that we are missing in this conversation. So there will be multiple in both sides. The only thing I see that is common between both the two parts of the market is the choice of propellant. Like they are converging with the kind of propellant they want. For example, in chemical propulsion, they want greener and greener propellants. So that's the route for everyone because they don't want hydrogen any longer.
Hydrogen is a very big problem.
Exactly. So regarding electric propulsion, of course, on the top of my mind comes like 4 technologies that will win the market, but we are missing all the chemical parts. So yes, we are missing a big slice of the pie. Like we are like doing the counting without a big part. So chemical propulsion is not ended. Like we know that electric propulsion is growing a lot, but chemical propulsion is still the leader of the market. So I wouldn't say something too big like, oh no, 1, 2 technologies. No, we are doing the counting without a big part. That's the problem in this conversation.
Yes,
so this is different. Well, we are biased because we have both, but yes. So, but that's also one of the reasons why we keep following both sides, because we don't believe there will be one winning over the other.
Yes, sure. But we are no racist. We also love chemical propulsion. It's not a problem.
We all love it.
Okay, thank you very much. Thank you to everybody. It's almost 5 p.m. so the time is it's very short. I think that we do not have time for other questions. So thank you very much to everybody. Thank you very much for this very high level roundtable. It was a very good roundtable, good discussion, a very good moment. So thank you very much, and maybe I let now Laurent or Stéphane finish the day with some word. And so thank you very much to everybody.
Thank you. Bye.
Thanks a lot, guys. Thanks a lot.
Thank you so much.
Thank you so much.
Thanks a lot. Thanks a lot, guys.
Bye. Okay. So it's time to do the closure ceremony or the conclusion, let's say, for this about this fifth MPCS workshop. So I will share my screen and I will do it most quickly. And okay. Okay, you see my screen? Yes, so first of all, that as in the organizing committee, what we want to thank Marlène Giamporcaro from INP from Toulouse for the huge work making possible the realization of this virtual edition of MPCS number 5. So just to let us know that the total attendee of people was 75 people from 14 different countries. So we obviously want to acknowledge all the sponsors of this workshop, Exotrail, TrustMe, Comat Aerospace, Oracle, Yenai Space companies, and the CNES Agency and Laplace and ICAR laboratories. And so we have, during these 3 days, a very fruitful and stimulating discussions through the overview of activities of companies involved in the domain. And we have seen some very new scientific knowledge for miniaturized thrusters, pulse, radio frequency, field emission, and all thrusters. And also including plasma satellite interactions with the topics this morning of plasma antenna, which is a new topic, I think, in the field of in the community, in the EP, in the electric propulsion community. So that's very a new topic and very important issue, I think, for the future. During this conference, we had 2 round tables. The first one was a scientific table yesterday. So very quick conclusion about that. So what we have seen is the importance of understanding of physics of the thruster operation through experimental and simulation. And if they can work together, obviously that is better. We have talked about and we have highlighted the role of plasma wall interactions since you reduce the surface to volume ratio. So it's very, and you have more and more plasma wall interaction in this small scale system. And maybe it would be useful just to explore also the combination between propellant and wall material for higher performances. Concerning the technological roundtable, we have seen just a few minutes ago. So some questions have been addressed. So I make a list here. So the first question was about the evolution of CubeSat, and very actually the conclusion was that there is some needs towards 6 to 12U and even 16U, bigger size satellites on the weight on the order between 50 to 100 kilograms. And there is also a market for the application of small propulsion system for scientific missions in deep space, just for example, around planets or asteroids. Another question was a bit about the deal between simplicity versus performance. That was a critical issue for these small size thrusters. And finally, I think that the conclusion was that it depends obviously on missions. Finally, you need for your system, for your propulsion system. And I would say maybe one of the biggest questions that we can ask in the community is that the market is big enough just to all technologies that we have seen during this workshop. And finally, the conclusion will be maybe 3 or 4 mature technologies will stay at the end, almost from the electric propulsion part, because chemical propulsion is obviously still present in for CubeSat, for propulsion of CubeSat satellites. So is there any maybe question or comment in the audience before I continue? Okay, if not, let me now switch to the.
You've got one for Miguel.
Ah, sorry, I did not. Yeah, please, Igal. I think it's. I don't have any rights just to give him.
Alberto has to transfer you the rights.
Yes.
Sorry, Stéphane?
Tu dois transférer les droits à Laurent pour qu'il soit animateur.
Ah oui, pardon. C'est bon.
And I don't see Igal. Sorry.
He disappeared.
Participants is here. Okay, sorry. Igal.
Hey guys,
yeah,
I want to say it's a great it was a great conference in this limited platform we have, but I think you made it very interesting. Unfortunately, I missed the panel. But I think I have a question maybe that interests a lot of also companies about regulations. So I don't know if you discussed this or not, but what is going on with the regulation things? That means like what will be the new regulations? I understand that like now debris, space debris and so on becomes very important with the huge number of satellites. Is there any change in regulation or expected change in regulation?
Nothing is clear yet. So the question has not been answered in the round table, but we had a comment from Davina Diquera from ESA saying that indeed the way the market will change and evolve in the future strongly depends also on the new rules and the new regulations. But nothing is very clear at the moment.
So it stays this 25-year rule, basically.
That's what I think currently, yes. Nothing is clearly established.
Yeah, I heard some other things that there is, I don't remember the exact committee in the UN, but they are debating this requirement for maneuvering or collision avoidance for any satellite. This is something that I heard about.
It's pretty obvious that with constellation and mega constellation, things are going to change in the future. But currently, there is a kind
We're already in the future.
Yeah, but probably in the near future, because we cannot go on that way for sure.
Yeah.
Maybe Alberto, you want to comment on that?
Yes, but the regulation topic is a very complex topic. The regulation is evolving now, so it's complicated to give you a precise answer today, because it's complicated to have a long-term vision now about this. But in the domain of micropropulsion, or space propulsion, generally speaking, the topic of, for example, the orbiting. It's a very important topic now, and we work, for example, at CNES, we work on these. We have some project on this.
Yeah, okay, I can imagine.
Okay, thank you.
Other comments?
Maybe
David?
if I can.
Yeah, Davina, please.
Yes, from his side. Yes, of course, we are paying attention on the evolution of this regulation. We are involved in this evolution, but nothing is certain at the moment. We see that with the advent of constellation and the population of LEO, of all the CubeSat, microsat, etc., things might get complicated in the future. And we heard about also possibility or demand of implementing mandatory propulsion for collision avoidance and disposal. Having said that, nothing is written black and white. What we believe is our responsibility as agency is to make sure that the technology will be ready at that point. So that's what we are trying to put attention with building the roadmap together with the other national agency and industry all together, because when the time comes, we will want to see the European product ready to answer the demand. So that's what, as agency, I believe is our responsibility.
Other comments on that specific point? Okay, so I continue. So thank you, Igal, for your comment. Yeah, we did not address this point during the roundtable. So all the talks will be available soon on a YouTube channel, and the links are indicated on the MPCS website. But we need some agreements, so we send you an email. I think also during the talk I think yesterday, there is also some question about what about the slides. I mean, what about the diffusion of the slides? So we don't have any answer now, I would say. Maybe in the same email, we can also ask this question about the slides. Okay. And finally, now we have to think to the next MPCS in 2 years, hopefully in person, we hope. And then candidature are welcome for the next MPCS, the 6th one. So that was our conclusion for that workshop. So the virtual edition, I would say, of the 5th MPCS workshop. Okay, so thank you to all of you. Thank you to all the speakers and all the attendees for the discussion, for the panel from Roundtable, and thank you to everybody for coming.
Yeah,
okay.
Thanks to all guys for making this workshop quite a great event, despite the fact it was a virtual edition. I'm really eager to attend the next one in 2023, as Laurent said, in person. But thanks again to everybody, and
thank you.
Big thanks to Marlène for his help and his involvement in the preparation of this event.
Yeah. Okay. So. Okay. Okay. Thank you to all of you. So I think that we can close the session.
Yeah, unless there is remark from the audience. Christophe, thanks.
Bye-bye.
Thanks a lot, Christophe.
Thank you. Thank you.
Thank you.
Thank you, all of you.
Thanks.
Bye. Thanks.
Thanks a lot. Bye.
Bye.
Bye. Bye. Bye.
Bye.
Thank you very much. Bye-bye.
Thank you, Davina,
Bye-bye.
for joining.
Okay, Davina. Thanks, Daniel.
Bye. Bye.
Finn, thanks.
Bye. Thanks, Daniel.
Il faut arrêter aussi la vidéo, c'est ça?
Thanks, Arturo.